When NASA's Voyager spacecraft reached the very edge of the solar system, at the place called the heliopause, they entered a strange zone nicknamed the Wall of Fire. In this region, the temperature shoots up to tens of thousands of degrees, ranging from about 30,000 to 50,000 Kelvin, sometimes even higher. This happens because the solar wind, a constant flow of charged particles coming from the sun, crashes into the interstellar medium, which is the thin spread of gas and dust that lies between stars. The collision makes the particles there heat up to extreme levels, creating this fiery barrier. But even though the temperatures are incredibly high, the Voyagers did not overheat. That's because the particles in this zone are spread out so thinly that there are too few of them to actually transfer heat to the spacecraft. Before we delve into the discoveries Voyager made, we would appreciate if you could like the video and comment below where you're watching from and what time it is for you. Now, settle in for a journey to the very edge of the solar system. Voyager 1 was launched on the 5th of September in the year 1977, and Voyager 2 had taken off earlier, on the 20th of August of that same year. The launches came only weeks apart, like siblings setting out on journeys that would eventually take them to different parts of the solar system and far beyond. Both spacecraft were built by the Jet Propulsion Laboratory in California, under the direction of NASA, and their purpose was clear. They were to explore the giant planets that circled far from the Sun, planets that until then had only been seen as blurry spots of light through telescopes. The Voyagers were designed to fly past Jupiter and Saturn, capturing pictures and gathering information. But there was a rare opportunity that made these missions even more ambitious. In the 1970s, the outer planets were arranged in such a way that a spacecraft could use their gravity to slingshot itself from one planet to the next, saving fuel and gaining speed each time. This chance alignment would not happen again for another 176 years. Scientists realized that if they launched the spacecraft at the right moment, one Voyager could visit Jupiter, Saturn, Uranus and Neptune in a single journey. This was called the Grand Tour, and it was one of the boldest plans ever attempted in the history of space exploration. Voyager 2 was given the path for the Grand Tour, while Voyager 1 was set on a course to fly by Jupiter and Saturn, before continuing on a different trajectory that would eventually send it out of the solar system at a higher speed. Though Voyager 1 was launched after Voyager 2, it travelled faster and overtook its twin in space, reaching Jupiter first. From the very beginning, the missions carried a sense of urgency, daring and wonder, because no one knew exactly what they would find. When Voyager 1 reached Jupiter in early 1979, humanity saw the planet as if for the first time. The spacecraft sent back breathtaking images of the Great Red Spot, a storm larger than the Earth that had been raging for centuries, and it revealed Jupiter's atmosphere to be a swirling, violent place of storms and currents, far more complex than anyone had imagined. But the biggest surprises came from the planet's moons. Until then, scientists had thought of Jupiter's moons as cold, dead rocks circling a giant planet. Voyager showed something entirely different. Io, one of Jupiter's largest moons, was discovered to be volcanically active, with eruptions that shot material hundreds of kilometers into space. This was the first time active volcanoes had been observed anywhere beyond Earth. The discovery shocked the scientific world because it proved that the solar system was still alive with geological activity in places no one had expected. Europa, another of Jupiter's moons, revealed a smooth, icy surface crisscrossed with cracks, suggesting the possibility of a liquid ocean beneath the ice. Suddenly, scientists were faced with the possibility that beneath that frozen shell might be an environment where life could exist. Ganymede and Callisto also turned out to be more complex than expected, with signs of geological processes that hinted at rich and varied histories. After leaving Jupiter, Voyager 1 travelled towards Saturn, arriving in late 1980. Once again, the spacecraft revolutionized what we knew. Saturn's rings, which had appeared as a simple structure through telescopes, were revealed to be intricate, made of countless ringlets, each one composed of icy particles ranging in size from tiny grains to massive chunks. Voyager 1 also discovered strange features like spokes that seemed to appear and disappear mysteriously across the rings. Saturn's moons offered more surprises. Titan, the largest moon, was found to have a thick atmosphere rich in nitrogen, thicker even than Earth's. This atmosphere hid the surface from Voyager's cameras, but its very existence raised profound questions about what might lie beneath. Voyager 2 followed behind and added more detail to everything its twin had found, but it also pressed on, venturing farther than any spacecraft before it. In 1986, Voyager 2 reached Uranus, the first and only time a spacecraft has visited the planet. There it revealed a strange, tilted world lying almost on its side, with a pale blue colour caused by methane in its atmosphere. Voyager 2 found that Uranus had faint rings and a system of moons, each one with unique and peculiar features. Miranda, for example, looked like a patchwork of terrains, as if pieces of different worlds had been stitched together. 4 years later, in 1989, Voyager 2 reached Neptune, the last planet in the Grand Tour. Once again, it uncovered wonders no one had expected. Neptune's atmosphere turned out to be active, with a massive storm called the Great Dark Spot, rivaling Jupiter's red spot in size. The planet's largest moon, Triton, stunned scientists with geysers that spouted nitrogen gas, another sign that the solar system held more dynamic and surprising worlds than anyone had believed. Triton also orbited Neptune in the opposite direction of the planet's rotation, hinting that it may have been captured long ago from elsewhere in the solar system. By the early 1990s, the planetary part of the Voyager missions had ended, but the spacecraft continued their journeys outward. Their instruments kept recording data about the environment of the outer solar system, and their antennas kept sending faint signals back to Earth. Engineers had to carefully manage the spacecraft, conserving power and finding creative ways to keep them alive, because no one had expected them to last this long. One of the most famous moments came in 1990 when Voyager 1, at the request of astronomer Carl Sagan, turned its camera back toward Earth and captured the image now known as the pale blue dot. From a distance of more than 6 billion kilometers, Earth appeared as a tiny speck, smaller than a pixel, suspended in a sunbeam. As the years passed, the Voyagers kept going. They moved into regions of space where the sun's influence began to weaken, regions no spacecraft had ever reached before. Scientists were eager to study the boundary between the solar system and interstellar space, the area where the solar wind from the sun met the particles and magnetic fields from the rest of the galaxy. Voyager 1 crossed this boundary, known as the heliopause, in the year 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in the year 2018, making the United States the first nation to send not one but 2 spacecraft beyond the solar system. Even after more than 4 decades, both Voyagers continue to send back information. Their instruments measure cosmic rays, magnetic fields, and the density of particles in space, giving scientists precious data about a region that had never been directly explored before. Every year that passes, the spacecraft venture farther into the unknown, carrying with them not only scientific instruments, but also a message from Earth. Each Voyager carries a golden record, a phonograph record coated in gold, designed to last for billions of years. On these records are sounds and images from Earth, chosen to represent the diversity of life and culture on our planet. They include greetings in dozens of languages, music from around the world, sounds of nature like bird song and ocean waves, and pictures of landscapes, people, and animals. The Golden Record was humanity's way of saying, "This is who we are," a time capsule launched into the stars in case the spacecraft were ever found by another civilization. The making of the Golden Record was itself an extraordinary effort. Carl Sagan and his team had to decide what message to send on behalf of all humankind, knowing that it might be the only chance to communicate with distant beings. They debated over what to include, choosing carefully so that the record would be both a scientific and cultural snapshot of Earth in the 20th century. The fact that the records exist turns the Voyager spacecraft into more than machines. They are cultural artifacts, symbols of our desire to reach beyond ourselves and be remembered across the cosmos. The durability of the Voyagers is part of what makes their story so remarkable. Built with 1970s technology, their computers are millions of times less powerful than the phones people carry in their pockets today, yet they continue to function and send back information across distances that are almost impossible to imagine. The signals they send take more than 20 hours to reach Earth, travelling at the speed of light. Scientists and engineers who manage the mission must plan carefully, often waiting almost 2 days for a command to be sent and the spacecraft's reply to be received. When the twin spacecraft began their long trek away from Earth and toward the distant planets, they carried not only cameras and instruments, but also the collective hopes of humanity to see realms that had never been seen before. Their mission was to venture farther than any spacecraft had ever gone, using clever maneuvers and the natural pull of gravity to slingshot from one giant world to the next. This journey across the solar system would bring them close to the enormous planet Jupiter, the majestic rings of Saturn, the pale blue Uranus, and the mysterious deep blue Neptune. Each encounter would reveal wonders that scientists had never imagined, and each world would tell its own story of storms, moons, rings, and strange phenomena that filled the imagination with awe. The path to Jupiter was the first great step. It was not just a planet waiting in the darkness, it was a colossal world, more massive than all the other planets combined, with a swirling atmosphere filled with violent storms and colours that looked like brushstrokes across a canvas. As the spacecraft approached, Jupiter's sheer size became overwhelming. Seen through the cameras, the planet filled more and more of the frame until it dominated the view like a giant painted globe spinning in endless motion. The closer the probes drew, the clearer the details became. The famous Great Red Spot, which astronomers had long seen through telescopes as a reddish oval, now appeared in astonishing detail. It was not a static mark, but a raging storm larger than Earth itself, a hurricane that had been spinning for centuries without rest. Within the storm were smaller swirls, eddies and turbulent currents, like waves in an endless ocean of gas. The spacecraft also revealed that Jupiter's atmosphere was not simply brown and red bands, but a living, moving system of clouds. White ovals formed and dissolved, darker patches stretched across its belts, and lightning flickered within hidden depths. The atmosphere was alive, restless, and constantly reshaping itself. Scientists who had once thought of Jupiter as a static world realized it was one of the most dynamic places in the solar system. But Jupiter was not only a planet, it was also a kingdom of moons. When the spacecraft flew past, it turned its cameras on the 4 largest moons discovered by Galileo centuries earlier. These moons, known as the Galilean moons, were worlds in their own right, each one unique. Io, the closest of the 4, stunned everyone. Instead of a quiet, frozen moon like those around other planets, Io was alive with fire and fury. The spacecraft saw active volcanoes erupting, spewing fountains of molten material high above its surface. Bright plumes stretched hundreds of kilometers into space, and lava lakes glowed like fiery wounds on its crust. It was the most volcanically active body in the entire solar system, a place of constant renewal and destruction. Nobody had expected such a world. Europa, by contrast, was quiet and mysterious. Its surface looked like cracked ice, crisscrossed by long ridges and grooves that seemed to stretch endlessly. Beneath this icy shell, scientists began to suspect there might be an ocean of liquid water kept warm by the pull and flexing caused by Jupiter's gravity. The thought that beneath Europa's frozen surface there could be a hidden ocean sparked the imagination. For where there is water, there might also be the possibility of life. Ganymede, the largest moon in the solar system, was revealed in detail for the first time. Bigger than the planet Mercury, it was a giant world covered with grooved terrain, dark patches and lighter icy regions. Its surface told a story of geological change, as if enormous forces had reshaped its crust over time. Scientists later discovered that Ganymede had its own magnetic field, the only moon known to have one, making it even more unusual. Callisto, the outermost of the 4, appeared ancient and heavily scarred with craters. Its battered surface suggested it had been left largely unchanged for billions of years, a frozen relic of the early solar system, holding secrets about its earliest days. After revealing the marvels of Jupiter and its moons, the spacecraft used the planet's immense gravity as a slingshot to propel themselves further outward. The next great destination was Saturn, the jewel of the solar system. Saturn had long captured human imagination with its glowing rings, but no telescope on Earth had ever shown them in such detail. As the spacecraft approached, Saturn's rings transformed from faint bands into an intricate system of countless icy particles orbiting the planet in delicate harmony. Through the cameras, the rings were no longer flat lines, but grand structures made of billions of icy fragments, some no bigger than grains of sand and others as large as mountains. They sparkled like diamonds as they caught the sunlight. The probes revealed that the rings were divided into many sections, with gaps and waves that looked almost like the grooves on a record. These patterns were shaped by the gravity of Saturn's moons, which tugged on the ring particles and carved out divisions. Saturn itself was no less breathtaking. Its atmosphere was wrapped in golden hues and swirling patterns. Enormous storms raged in its cloud tops, and winds blew faster than any on Earth. Unlike Jupiter's bright great red spot, Saturn had subtler but equally fascinating features, including vast hexagonal shapes at its north pole that looked almost like a perfect geometric design carved into the atmosphere. Among Saturn's moons, one stood out as the most remarkable: Titan. Shrouded in a thick orange haze, Titan was a world that seemed strangely familiar. The spacecraft could not see its surface directly because of the dense atmosphere, but instruments detected methane and other organic molecules. Titan was the only moon with a thick atmosphere, and it seemed to have processes similar to Earth's, with possible lakes, rivers and rain, not of water but of methane and ethane. It was a world that seemed like a frozen mirror of Earth, with landscapes shaped by liquids under an alien sky. Another moon that captured attention was Enceladus, a small icy body that, to the surprise of scientists, reflected nearly all the sunlight that struck it. Its brilliant white surface suggested it was covered in fresh ice, and later evidence showed geysers erupting from its south pole, spraying plumes of water into space. Though the spacecraft only caught hints of this phenomenon, it became one of the most fascinating discoveries of the Saturnian system. Once again, Saturn's gravity gave the spacecraft the momentum to continue their odyssey. This time the path led to Uranus, a planet that until then had been little more than a pale green dot in telescopes. The journey took many years, and when the spacecraft finally arrived, Uranus revealed itself as one of the strangest planets in the solar system. Unlike other planets, which rotate more or less upright, Uranus lay tilted on its side, spinning almost like a ball rolling around the sun. This odd tilt gave it extreme seasons, with one pole facing the sun for decades before turning into decades of darkness. Seen up close, Uranus was calm and bluish-green, its colour caused by methane in its atmosphere. Unlike Jupiter and Saturn, it seemed to lack the same dramatic bands and storms. Its surface looked featureless at first, almost tranquil, but the spacecraft detected subtle cloud patterns and faint signs of activity. Around it, the probes found a system of faint rings, much darker and narrower than Saturn's but still fascinating, circling the tilted planet in thin arcs. Uranus also had a collection of moons that proved to be far more interesting than anyone had expected. Miranda, one of the smallest of its major moons, looked like a patchwork world, as if pieces of different places had been stitched together. Giant cliffs towered above its surface, some taller than Mount Everest on Earth, and strange ridges and valleys crisscrossed it in bizarre patterns. Scientists could hardly believe such a small moon could have such dramatic landscapes. Other moons like Oriole, Umbriel, Titania, and Oberon each revealed their own mysteries, with craters, canyons, and icy surfaces that hinted at histories of geological activity. These moons, once thought to be mere specks, turned out to be dynamic worlds with unique features. From Uranus, the spacecraft continued their flight to Neptune, the last of the giant planets. Neptune lay so far from the Sun that it received only a fraction of the light and warmth that Earth did, yet it was a world of great activity. When the spacecraft arrived, Neptune appeared deep blue, richer in colour than Uranus, with swirling clouds and the fastest winds in the solar system. Neptune also had a remarkable moon, Triton, which stunned everyone who saw the images sent back. Unlike most moons, which orbit their planets in the same direction the planet spins, Triton moved in the opposite direction, suggesting it had once been captured by Neptune's gravity rather than formed beside it. Triton's surface was unlike anything else seen before: icy plains, frozen lakes, strange ridges, and even geysers that erupted nitrogen gas into space. It was a world of cold beauty, with hints of activity despite the frigid temperatures. The spacecraft showed that Neptune, though distant and dim, was far from lifeless. It was a planet of motion, winds, and a moon that seemed alive with changes. After completing their encounters with the 4 giant planets, the spacecraft continued their paths outward, leaving the familiar realms of the planets and heading toward the vast frontier beyond. Their journey across the solar system had revealed Jupiter's storms and fiery moons, Saturn's rings and hazy Titan, Uranus's tilted world and patchwork moons, and Neptune's dark storms and icy Triton. The heliosphere can be imagined as a giant bubble surrounding our solar system, and this bubble is not made of air or water, but of charged particles, streams of energetic matter that come from the Sun itself. To understand how this strange bubble works, it helps to think about the Sun not just as a shining ball of light that gives heat and energy, but as a restless, powerful star that is constantly throwing material into space. The Sun gives off something called the solar wind, which is made of tiny charged particles, mostly protons and electrons, and this flow of particles never stops. Day and night, year after year, century after century, the Sun keeps breathing out this invisible wind, and because of this constant flow, the solar wind pushes outward into the vastness of interstellar space. The result is a kind of shield or bubble that surrounds all the planets, moons, comets, and asteroids that orbit the Sun. This invisible protective region is what scientists call the heliosphere. The heliosphere is not small. It stretches unimaginably far away from the Sun, much farther than the distance to the outermost planet, Neptune. While Earth is only 1 astronomical unit away from the Sun, which means about 93 million miles, the boundary of the heliosphere can be more than 100 times that distance. Imagine a soap bubble floating in the air, with the Sun at the centre, and around it the bubble grows larger and larger until it forms a massive shield that separates the inside of the solar system from the galaxy outside. That is what the heliosphere is, except instead of being made of soap film, it is made of energy and charged particles. The way the heliosphere forms is simple to describe but incredibly complex in detail. The Sun's solar wind rushes out in every direction. At first, when the solar wind is near the Sun, it is very fast, travelling at hundreds of miles per second. Far faster than any rocket humanity has ever built. As it moves outward, it keeps going until it meets the space between the stars, which scientists call the interstellar medium. The interstellar medium is not empty. It is filled with extremely thin gas, dust, and cosmic rays from faraway stars and supernovas. When the solar wind collides with this interstellar medium, something remarkable happens. The two forces push against one another. The solar wind tries to expand outward, while the material of interstellar space pushes inward. The balance between these two pressures creates the surface of the heliosphere. The heliosphere is not a perfect sphere, even though the name might make you think of something perfectly round. Instead, it is shaped more like a teardrop or a comet, with a rounded front facing the direction that the solar system is moving through the galaxy, and a long tail stretching behind it. The reason for this shape is the movement of the solar system itself. The Sun, along with all the planets, is moving around the centre of the Milky Way galaxy at a speed of hundreds of thousands of miles per hour. Because of this movement, the bubble of the heliosphere is compressed in front, where the solar wind pushes directly into the interstellar medium, and stretched out behind, where the solar wind trails off like the tail of a comet. This enormous structure travels with us as we orbit around the galaxy, carrying everything in the solar system within it. Inside the heliosphere, life on Earth enjoys protection from some of the most dangerous forces in the universe. Outside of the heliosphere, cosmic rays fill interstellar space. These cosmic rays are high-energy particles that can damage living tissue and disrupt electronic systems. Without the shield of the heliosphere, Earth would be bombarded by a much higher dose of cosmic radiation. The heliosphere acts like a barrier, slowing down and deflecting many of these rays. It does not stop all of them, but it reduces the amount that reaches the planets, making it possible for life to survive and evolve in relative safety. The Earth's own magnetic field and atmosphere add another layer of protection, but the heliosphere is the first and largest shield, extending far beyond Earth, Jupiter, and even Pluto. The exact size of the heliosphere is not fixed. Because the solar wind itself changes with the sun's activity, the heliosphere grows and shrinks over time. Every 11 years, the sun goes through a cycle of activity, sometimes becoming more active with solar flares and coronal mass ejections, and sometimes calming down. When the sun is more active, the solar wind is stronger, and the heliosphere pushes farther outward into space. When the sun is less active, the solar wind weakens, and the heliosphere contracts inward. On even longer timescales, as the sun ages over billions of years, the character of the solar wind changes as well, which means the shape and power of the heliosphere are always shifting. When spacecraft such as the Voyagers travelled outward from Earth, they eventually reached the edges of this bubble. What they discovered was both fascinating and surprising. The boundary of the heliosphere is not just one clear surface, like the wall of a room, but a series of complex layers. The first of these is called the termination shock. This is the region where the solar wind, which was moving at supersonic speeds, suddenly slows down because it collides with the interstellar medium. Imagine a fast-flowing river running into a still lake. When the river meets the lake, the water slows down and forms waves and turbulence. The same thing happens at the termination shock, where the solar wind suddenly loses much of its speed and becomes hotter and denser. Beyond the termination shock lies the heliosheath, a vast zone of turbulent, slowed-down solar wind that continues to press outward against interstellar space. The heliosheath is like a thick outer layer of the bubble, a place of swirling currents, eddies, and magnetic chaos. The solar wind particles here are mixed and churned, and cosmic rays from outside begin to leak in, creating a strange and active environment. Farther out still lies the heliopause, the true boundary of the heliosphere. This is the surface where the pressure of the solar wind and the pressure of the interstellar medium balance each other. At the heliopause, the solar wind can go no farther, and interstellar space begins. It is here that the bubble of the sun ends and the larger galaxy takes over. The heliosphere is not visible to the human eye. If you were riding on a spacecraft moving outward through the solar system, you would not see a shimmering wall marking its edge. Instead, the boundaries of the heliosphere are invisible and can only be detected by measuring changes in particle densities, magnetic fields, and cosmic ray intensities. The Voyager spacecraft, launched in the year 1977, were the first to give us direct data from these faraway regions. When they crossed the termination shock and later the heliopause, their instruments recorded dramatic changes, revealing that they had left the realm of the sun's influence and entered true interstellar space. The study of the heliosphere is not just about curiosity. It has practical importance for human exploration of space. Future astronauts travelling beyond the protection of Earth's magnetic field will rely on the heliosphere's shield against cosmic radiation. Understanding how strong this protection is, how much it changes, and where its edges lie is vital for planning safe journeys. Moreover, the heliosphere also gives us insight into the nature of stars in general. Our Sun is just one among billions of stars in the Milky Way, and many of those stars produce their own stellar winds and form their own astrospheres, which are bubbles similar to the heliosphere. By studying our own bubble, we learn about the bubbles of other stars, and therefore about the environments of planets orbiting them. One striking way to think of the heliosphere is as the frontier of our solar system. Within its borders lie all the planets, moons, and the familiar territory of the Sun's domain. Beyond its borders lies the unknown ocean of the galaxy. Just as ancient sailors once left the safety of coastal waters and ventured into open seas, so spacecraft like Voyager have left the comfort of the heliosphere and crossed into interstellar waters. The fact that humanity has even reached this boundary is an astonishing achievement, given that it lies tens of billions of miles away from Earth. The heliosphere is also shaped by magnetic fields. The solar wind carries with it the sun's magnetic field, dragging it outward into space. As the sun rotates, this magnetic field becomes twisted into a spiral shape, known as the Parker spiral. This spiral fills the heliosphere and influences the motion of charged particles within it. At the boundaries, the interaction of the solar magnetic field with the galactic magnetic field creates complex and dynamic regions. Magnetic reconnection, turbulence, and shock waves all play roles in shaping the edge of the heliosphere. These invisible forces, though they cannot be seen directly, govern the structure of the sun's protective bubble. Cosmic rays provide another fascinating connection to the heliosphere. When supernova explosions send high-energy particles racing through the galaxy, many of them head toward our solar system. Through the cameras, the rings were no longer flat lines, but grand structures made of billions of icy fragments, some no bigger than grains of sand and others as large as mountains. They sparkled like diamonds as they caught the sunlight. The probes revealed that the rings were divided into many sections, with gaps and waves that looked almost like the grooves on a record. These patterns were shaped by the gravity of Saturn's moons, which tugged on the ring particles and carved out divisions. Saturn itself was no less breathtaking. Its atmosphere was wrapped in golden hues and swirling patterns. Enormous storms raged in its cloud tops, and winds blew faster than any on Earth. Unlike Jupiter's bright great red spot, Saturn had subtler but equally fascinating features, including vast hexagonal shapes at its north pole that looked almost like a perfect geometric design carved into the atmosphere. Among Saturn's moons, one stood out as the most remarkable: Titan. Shrouded in a thick orange haze, Titan was a world that seemed strangely familiar. The spacecraft could not see its surface directly because of the dense atmosphere, but instruments detected methane and other organic molecules. Titan was the only moon with a thick atmosphere, and it seemed to have processes similar to Earth's, with possible lakes, rivers and rain, not of water but of methane and ethane. It was a world that seemed like a frozen mirror of Earth, with landscapes shaped by liquids under an alien sky. Another moon that captured attention was Enceladus, a small icy body that, to the surprise of scientists, reflected nearly all the sunlight that struck it. Its brilliant white surface suggested it was covered in fresh ice, and later evidence showed geysers erupting from its south pole, spraying plumes of water into space. Though the spacecraft only caught hints of this phenomenon, it became one of the most fascinating discoveries of the Saturnian system. Once again, Saturn's gravity gave the spacecraft the momentum to continue their odyssey. This time the path led to Uranus, a planet that until then had been little more than a pale green dot in telescopes. The journey took many years, and when the spacecraft finally arrived, Uranus revealed itself as one of the strangest planets in the solar system. Unlike other planets, which rotate more or less upright, Uranus lay tilted on its side, spinning almost like a ball rolling around the sun. This odd tilt gave it extreme seasons, with one pole facing the sun for decades before turning into decades of darkness. Seen up close, Uranus was calm and bluish-green, its colour caused by methane in its atmosphere. Unlike Jupiter and Saturn, it seemed to lack the same dramatic bands and storms. Its surface looked featureless at first, almost tranquil, but the spacecraft detected subtle cloud patterns and faint signs of activity. Around it, the probes found a system of faint rings, much darker and narrower than Saturn's but still fascinating, circling the tilted planet in thin arcs. Uranus also had a collection of moons that proved to be far more interesting than anyone had expected. Miranda, one of the smallest of its major moons, looked like a patchwork world, as if pieces of different places had been stitched together. Giant cliffs towered above its surface, some taller than Mount Everest on Earth, and strange ridges and valleys crisscrossed it in bizarre patterns. Scientists could hardly believe such a small moon could have such dramatic landscapes. Other moons like Oriole, Umbriel, Titania, and Oberon each revealed their own mysteries, with craters, canyons, and icy surfaces that hinted at histories of geological activity. These moons, once thought to be mere specks, turned out to be dynamic worlds with unique features. From Uranus, the spacecraft continued their flight to Neptune, the last of the giant planets. Neptune lay so far from the Sun that it received only a fraction of the light and warmth that Earth did, yet it was a world of great activity. When the spacecraft arrived, Neptune appeared deep blue, richer in colour than Uranus, with swirling clouds and the fastest winds in the solar system. Neptune also had a remarkable moon, Triton, which stunned everyone who saw the images sent back. Unlike most moons, which orbit their planets in the same direction the planet spins, Triton moved in the opposite direction, suggesting it had once been captured by Neptune's gravity rather than formed beside it. Triton's surface was unlike anything else seen before. Icy plains, frozen lakes, strange ridges, and even geysers that erupted nitrogen gas into space. It was a world of cold beauty, with hints of activity despite the frigid temperatures. The spacecraft showed that Neptune, though distant and dim, was far from lifeless. It was a planet of motion, winds, and a moon that seemed alive with changes. After completing their encounters with the 4 giant planets, the spacecraft continued their paths outward, leaving the familiar realms of the planets and heading toward the vast frontier beyond. Their journey across the solar system had revealed Jupiter's storms and fiery moons, Saturn's rings and hazy Titan, Uranus's tilted world and patchwork moons, and Neptune's dark storms and icy Triton. The heliosphere can be imagined as a giant bubble surrounding our solar system, and this bubble is not made of air or water, but of charged particles, streams of energetic matter that come from the Sun itself. To understand how this strange bubble works, it helps to think about the Sun not just as a shining ball of light that gives heat and energy, but as a restless, powerful star that is constantly throwing material into space. The Sun gives off something called the solar wind, which is made of tiny charged particles, mostly protons and electrons, and this flow of particles never stops. Day and night, year after year, century after century, the Sun keeps breathing out this invisible wind, and because of this constant flow, the solar wind pushes outward into the vastness of interstellar space. The result is a kind of shield or bubble that surrounds all the planets, moons, comets, and asteroids that orbit the Sun. This invisible protective region is what scientists call the heliosphere. The heliosphere is not small. It stretches unimaginably far away from the Sun, much farther than the distance to the outermost planet, Neptune. While Earth is only 1 astronomical unit away from the Sun, which means about 93 million miles, the boundary of the heliosphere can be more than 100 times that distance. Imagine a soap bubble floating in the air, with the Sun at the centre, and around it the bubble grows larger and larger until it forms a massive shield that separates the inside of the solar system from the galaxy outside. That is what the heliosphere is, except instead of being made of soap film, it is made of energy and charged particles. The way the heliosphere forms is simple to describe but incredibly complex in detail. The Sun's solar wind rushes out in every direction. At first, when the solar wind is near the Sun, it is very fast, travelling at hundreds of miles per second. Far faster than any rocket humanity has ever built. As it moves outward, it keeps going until it meets the space between the stars, which scientists call the interstellar medium. The interstellar medium is not empty. It is filled with extremely thin gas, dust, and cosmic rays from faraway stars and supernovas. When the solar wind collides with this interstellar medium, something remarkable happens. The two forces push against one another. The solar wind tries to expand outward, while the material of interstellar space pushes inward. The balance between these two pressures creates the surface of the heliosphere. The heliosphere is not a perfect sphere, even though the name might make you think of something perfectly round. Instead, it is shaped more like a teardrop or a comet, with a rounded front facing the direction that the solar system is moving through the galaxy, and a long tail stretching behind it. The reason for this shape is the movement of the solar system itself. The Sun, along with all the planets, is moving around the centre of the Milky Way galaxy at a speed of hundreds of thousands of miles per hour. Because of this movement, the bubble of the heliosphere is compressed in front, where the solar wind pushes directly into the interstellar medium, and stretched out behind, where the solar wind trails off like the tail of a comet. This enormous structure travels with us as we orbit around the galaxy, carrying everything in the solar system within it. Inside the heliosphere, life on Earth enjoys protection from some of the most dangerous forces in the universe. Outside of the heliosphere, cosmic rays fill interstellar space. These cosmic rays are high-energy particles that can damage living tissue and disrupt electronic systems. Without the shield of the heliosphere, Earth would be bombarded by a much higher dose of cosmic radiation. The heliosphere acts like a barrier, slowing down and deflecting many of these rays. It does not stop all of them, but it reduces the amount that reaches the planets, making it possible for life to survive and evolve in relative safety. The Earth's own magnetic field and atmosphere add another layer of protection, but the heliosphere is the first and largest shield, extending far beyond Earth, Jupiter, and even Pluto. The exact size of the heliosphere is not fixed. Because the solar wind itself changes with the sun's activity, the heliosphere grows and shrinks over time. Every 11 years, the sun goes through a cycle of activity, sometimes becoming more active with solar flares and coronal mass ejections, and sometimes calming down. When the sun is more active, the solar wind is stronger, and the heliosphere pushes farther outward into space. When the sun is less active, the solar wind weakens, and the heliosphere contracts inward. On even longer timescales, as the sun ages over billions of years, the character of the solar wind changes as well, which means the shape and power of the heliosphere are always shifting. When spacecraft such as the Voyagers travelled outward from Earth, they eventually reached the edges of this bubble. What they discovered was both fascinating and surprising. The boundary of the heliosphere is not just one clear surface, like the wall of a room, but a series of complex layers. The first of these is called the termination shock. This is the region where the solar wind, which was moving at supersonic speeds, suddenly slows down because it collides with the interstellar medium. Imagine a fast-flowing river running into a still lake. When the river meets the lake, the water slows down and forms waves and turbulence. The same thing happens at the termination shock, where the solar wind suddenly loses much of its speed and becomes hotter and denser. Beyond the termination shock lies the heliosheath, a vast zone of turbulent, slowed-down solar wind that continues to press outward against interstellar space. The heliosheath is like a thick outer layer of the bubble, a place of swirling currents, eddies, and magnetic chaos. The solar wind particles here are mixed and churned, and cosmic rays from outside begin to leak in, creating a strange and active environment. Farther out still lies the heliopause, the true boundary of the heliosphere. This is the surface where the pressure of the solar wind and the pressure of the interstellar medium balance each other. At the heliopause, the solar wind can go no farther, and interstellar space begins. It is here that the bubble of the sun ends and the larger galaxy takes over. The heliosphere is not visible to the human eye. If you were riding on a spacecraft moving outward through the solar system, you would not see a shimmering wall marking its edge. Instead, the boundaries of the heliosphere are invisible and can only be detected by measuring changes in particle densities, magnetic fields, and cosmic ray intensities. The Voyager spacecraft, launched in the year 1977, were the first to give us direct data from these faraway regions. When they crossed the termination shock and later the heliopause, their instruments recorded dramatic changes, revealing that they had left the realm of the sun's influence and entered true interstellar space. The study of the heliosphere is not just about curiosity. It has practical importance for human exploration of space. Future astronauts travelling beyond the protection of Earth's magnetic field will rely on the heliosphere's shield against cosmic radiation. Understanding how strong this protection is, how much it changes, and where its edges lie is vital for planning safe journeys. Moreover, the heliosphere also gives us insight into the nature of stars in general. Our Sun is just one among billions of stars in the Milky Way, and many of those stars produce their own stellar winds and form their own astrospheres, which are bubbles similar to the heliosphere. By studying our own bubble, we learn about the bubbles of other stars, and therefore about the environments of planets orbiting them. One striking way to think of the heliosphere is as the frontier of our solar system. Within its borders lie all the planets, moons, and the familiar territory of the Sun's domain. Beyond its borders lies the unknown ocean of the galaxy. Just as ancient sailors once left the safety of coastal waters and ventured into open seas, so spacecraft like Voyager have left the comfort of the heliosphere and crossed into interstellar waters. The fact that humanity has even reached this boundary is an astonishing achievement, given that it lies tens of billions of miles away from Earth. The heliosphere is also shaped by magnetic fields. The solar wind carries with it the sun's magnetic field, dragging it outward into space. As the sun rotates, this magnetic field becomes twisted into a spiral shape, known as the Parker spiral. This spiral fills the heliosphere and influences the motion of charged particles within it. At the boundaries, the interaction of the solar magnetic field with the galactic magnetic field creates complex and dynamic regions. Magnetic reconnection, turbulence, and shock waves all play roles in shaping the edge of the heliosphere. These invisible forces, though they cannot be seen directly, govern the structure of the sun's protective bubble. Cosmic rays provide another fascinating connection to the heliosphere. When supernova explosions send high-energy particles racing through the galaxy, many of them head toward our solar system. Without the heliosphere, they would strike Earth in much greater numbers, but the magnetic fields and charged particles of the heliosphere deflect and scatter them, acting as a shield. At times, when the Sun's activity is strong, this shielding effect is greater, and fewer cosmic rays reach Earth. At other times, when the Sun is weaker, more cosmic rays penetrate. This rhythm influences not only the radiation environment of space, but may even have subtle effects on Earth's climate over long periods. The sheer size of the heliosphere is difficult to grasp. Imagine a map of the solar system where Earth's orbit is represented as a small circle, then expand outward to include Mars, Jupiter, Saturn, Uranus and Neptune. All of these planets fit easily within the heliosphere, but even beyond Neptune's orbit, far past Pluto, the bubble extends for dozens of times that distance. If Earth's orbit were the size of a coin, the heliosphere would stretch out to the size of a large room. Within this enormous space, the solar wind rules, but beyond it, the forces of the galaxy dominate. The heliosphere also interacts with interstellar clouds. The solar system is not drifting through a perfectly empty void, but through a region of the galaxy filled with thin, diffuse clouds of gas. At present, the solar system is passing through a region known as the local interstellar cloud, which is relatively warm and diffuse. The pressure and density of this cloud affect the size and shape of the heliosphere. In the distant future, as the solar system moves into different interstellar regions, the heliosphere may change dramatically, growing larger or shrinking smaller depending on the conditions outside. To put this into a more human perspective, imagine that you are standing inside a giant balloon. The air inside the balloon is being constantly pumped in by a machine, keeping it inflated. Outside the balloon, winds are pressing against it, trying to collapse it. The size of the balloon depends on how strong the machine inside is compared to the winds outside. This is what happens with the heliosphere. The Sun pumps out the solar wind, inflating the bubble, while the interstellar medium presses against it from the outside. The balance between these forces decides the bubble's size and shape. Entering the unknown, the edge of the solar system, the heliosheath, has always been a place of deep mystery for scientists. For centuries, human beings looked at the night sky and wondered how far the reach of the Sun extended, how strong its invisible hand was, and where its influence ended. Long before spacecrafts existed, thinkers and astronomers imagined that the Sun was not only a giver of a light and heat, but also the source of a powerful stream of energy that rushed outward through all the space surrounding it. This stream of charged particles, which later came to be called the solar wind, was believed to blow outward in all directions until it finally met the great ocean of particles and radiation that fills the rest of the galaxy. The region where the solar wind slowed, bent, and fought against that outside ocean became known as the edge of the solar system, and the special outermost layer of this invisible bubble was called the heliosheath. The heliosheath is like a turbulent borderland, a place where two mighty forces wrestle and tangle together. On one side there is the solar wind, racing away from the Sun at hundreds of thousands of miles per hour, carrying magnetic fields and charged particles born in the fiery atmosphere of the Sun. On the other side there is the interstellar medium, the thin but endless soup of gas, dust and cosmic rays that drift between the stars. Scientists expected that where these two forces meet there would be chaos, storm-like turbulence, and strange forms of energy that had never been measured before. They believed the heliosheath would be like the churning foam at the edge of a great river where it meets the sea. When researchers studied this far-off frontier from Earth, they could only guess what would be found there. Telescopes gave only faint hints, radio signals revealed only vague shadows, and mathematical models could provide only imagined shapes. The actual boundary, they thought, would be full of shockwaves where the solar wind slows abruptly, eddies of magnetic energy twisting like whirlpools, and bursts of high-energy particles slamming into each other. The heliosheath, in their minds, was not a calm or gentle place, but a restless region where the Sun's power struggled against the weight of the galaxy itself. One of the great expectations about the heliosheath was that it would act as a giant shield. Scientists imagined it as a protective cushion, slowing and deflecting much of the dangerous cosmic radiation that rushes through interstellar space. Without this shield, Earth and the other planets would be bombarded by much stronger doses of high-energy particles, making life as we know it far more difficult. So, they thought that inside the heliosheath there would be a measurable drop in cosmic rays, with the magnetic fields carried by the solar wind weaving a tangled net that trapped or scattered these rays. If this shield worked as expected, then spacecraft that crossed into the heliosheath should still find protection, though weaker than inside the inner solar system. Another idea was that the heliosheath would contain structures shaped like bubbles or filaments, formed by the way magnetic fields twist and snap. The Sun's magnetic field is not steady. It flips every 11 years, and it waves and wobbles as it flows outward with the solar wind. By the time these magnetic patterns reach the edge of the solar system, they would be stretched and distorted, forming giant magnetic highways and valleys. Scientists pictured the heliosheath as being filled with such magnetic lanes, guiding charged particles along certain paths and blocking them from others. They imagined spacecraft moving through this region would detect sudden changes, like moving from one magnetic room into another. The turbulence of the heliosheath was also expected to create heat. As the solar wind slowed down after crossing the termination shock, the place where the wind first begins to lose its speed, its energy would not vanish, but instead churn into heat and disorder. The particles would bang against one another, creating a warmer but slower moving plasma. Instruments aboard probes would then measure higher temperatures, strange pressure waves, and swirling flows that seemed to have no clear direction. The heliosheath, they thought, was the Sun's stormy frontier, filled with invisible thunder. Some scientists expected that within this boundary there would also be a layer of trapped neutral atoms. These atoms would not be charged like the solar wind's particles, but they would be born when charged particles and interstellar atoms exchanged electrons. Such neutral atoms could slip across magnetic boundaries more easily, drifting into the inner solar system and providing subtle clues about the shape of the heliosheath. Years before probes reached this region, Earth-based instruments tried to detect these neutral atoms, and their faint signals suggested that the boundary might be more complex than a simple shell. The size of the heliosheath was also a question full of uncertainty. Some believed it might extend billions of miles beyond the orbit of Neptune, while others thought it might be compressed by nearby interstellar clouds. The solar system, after all, is not moving through empty space but through patches of gas and dust left over from ancient stars. If the Sun was ploughing into a denser region, the heliosheath would be squeezed, while if it was moving through thinner regions, the heliosheath might swell outward. This made the very shape of the boundary uncertain. Would it be a neat round bubble, or would it be a comet-like tail stretching behind the Sun as it moves through the galaxy? Many suspected the latter, picturing the heliosheath as the billowing wake of a ship sailing across a cosmic sea. There was also the question of shock waves. The solar wind sometimes erupts with bursts called coronal mass ejections, where giant clouds of plasma and magnetic energy are flung outward. These storms move faster than the regular solar wind and create shock fronts as they travel. Scientists thought that when these fronts reached the heliosheath, they would crash into the slower moving boundary and create turbulence on a massive scale. Spacecraft might then detect sudden surges of radiation or strange pulses of magnetic energy as these shocks reverberated through the region. The expected turbulence of the heliosheath made it seem like a natural laboratory for studying plasma physics, the science of charged gases. Plasma behaves in ways that are still not fully understood, often moving in tangled patterns that defy simple equations. The heliosheath, being so large and so energetic, would offer a grand stage for observing plasma behavior on a scale impossible to reproduce on Earth. Scientists dreamed that instruments carried by deep space probes would capture these effects directly, giving new insights into the fundamental forces that shape not only our solar system, but also countless other star systems across the galaxy. The heliosheath was also expected to act as a boundary for solar influence in a more poetic sense. Inside this zone, the Sun rules supreme, its wind pushing, its magnetism guiding, its storms shaping space itself. Beyond it, the stars rule, their cosmic rays flowing freely, their interstellar gases stretching far and wide. The heliosheath was imagined as a kind of twilight zone, where the familiar realm of the Sun gave way to the unknown sea between the stars. For many scientists, reaching and studying this place meant touching the edge of home and peering out into the foreign wilderness that surrounds it. When the twin Voyager spacecraft were launched in the year 1977, many researchers already looked ahead to the day when these explorers might reach the heliosheath. Though the missions were first designed to study Jupiter, Saturn, Uranus and Neptune, their paths would carry them ever outward. With luck, time and functioning instruments, they might one day pierce the edge of the solar system and send back data from the turbulent frontier. What would they find in the heliosheath? Would the solar wind behave as expected, or would new and stranger phenomena appear? The anticipation of these answers kept scientists restless for decades. Theorists built models using powerful computers, trying to simulate the clash of solar wind and interstellar medium. In these models, colourful maps showed waves of pressure, ripples of magnetic energy, and regions of high or low density. Some predicted that the heliosheath would be thick and chaotic, others suggested it might be surprisingly thin. Some even imagined that magnetic reconnection, where magnetic field lines snap and reconnect, would be common there, releasing sudden bursts of energy. All these possibilities made the heliosheath a treasure chest of mysteries waiting to be unlocked. There were also practical reasons for wanting to understand this region. Human beings dream of one day sending spacecraft far beyond the solar system, perhaps even crewed vessels. Knowing how much radiation and turbulence await at the edge is crucial for planning such journeys. If the heliosheath turned out to be far more hostile than expected, with dangerous surges of cosmic rays, then shielding future travellers would require greater preparation. If, on the other hand, it provided a smoother path, then the road to interstellar travel might be less threatening. Thus, the heliosheath was not only an object of scientific wonder, but also a stepping stone toward humanity's greater voyage into the galaxy. Scientists expected the heliosheath to also give answers about the Sun itself. By studying how the solar wind behaves at such extreme distances, they could learn more about how it begins near the Sun, how it evolves as it flows outward, and how it interacts with other stars' winds. The Sun is just one star among billions, yet by watching its wind at the boundary, astronomers hope to gain insights into how stars carve out space bubbles everywhere in the universe. The heliosheath, then, was like a test case, a close-up look at a universal process. They also thought the heliosheath might hide surprises about energy transport. When particles slow down, where does their energy go? Does it become heat? Does it transform into magnetic turbulence? Or does it leak into interstellar space? Such questions puzzled theorists, and the heliosheath offered a natural place to test answers. Some models suggested that much of the solar wind's energy would be lost in turbulence there, like waves crashing on a rocky shore. Others suggested that large-scale flows would carry energy smoothly into the galaxy. Measuring this balance was a goal of the probes that ventured outward. The idea of the heliosheath inspired not only scientific curiosity, but also a sense of wonder. To imagine a region so far away, billions of miles from Earth, where the invisible hand of the Sun still struggles against the breath of the galaxy, is to imagine a grand borderland. It is a place that no human eye can ever see directly, yet it surrounds us all, defining the extent of our cosmic neighbourhood. For generations, scientists expected it to be a place of storms and shields, a frontier where the familiar laws of solar physics meet the broader laws of interstellar space. And so, the expectations were built. Turbulence, shock waves, magnetic bubbles, heat, shielding, cosmic rays, and unexpected structures. Every idea painted the heliosheath as a restless and mysterious zone, not a quiet ending but a dramatic border. The spacecraft racing outward carried with them not only instruments, but also the hopes of those who wished to finally know what lay at the edge of the Sun's domain. When Voyager 1 and Voyager 2 first left Earth in the year 1977, their mission was to fly past the giant planets, Jupiter, Saturn, Uranus, and Neptune, and to send back pictures and data. At the time, nobody knew for sure how long they would last. The fact that they still worked decades later was itself a kind of miracle. Each probe carried a set of instruments to measure things like magnetic fields, cosmic rays, plasma, and radio waves. These tools were like senses, a way for the spacecraft to feel and listen to the invisible environment around them. As the years passed and the probes travelled billions of miles, scientists began to wonder whether they might one day actually reach the outer edge of the heliosphere, the place where the sun's influence faded and interstellar space began. Nobody knew exactly what would be there. Some thought the transition would be gradual, a smooth fading. Others imagined a sharp border, like stepping through a door. By the early 2000s, both Voyagers had gone far beyond Pluto's orbit. The sun's light was faint, and the planets were long behind them. What they were moving into was not empty nothingness, but a realm filled with invisible winds and particles that drifted between the stars. In 2012, Voyager 1 reported signs that it had crossed into interstellar space, though debates continued for years about the precise moment of crossing. But even before that, the spacecraft detected something strange. The charged particles of the solar wind, which normally streamed outward, began to slow down and pile up. It was as if the particles were being pressed against some unseen barrier. The magnetic fields, too, seemed to change direction in unexpected ways. It was in those years that talk of a wall at the edge of the heliosphere began. The word wall was not meant in the simple sense of a solid surface like a brick wall, but rather in the sense of an invisible boundary where forces gather and push back. Imagine wind blowing through a valley and then meeting a cliff face. The air piles up, forming turbulence, pressure, and eddies. In space, something like this seemed to be happening at the edge of the heliosphere. The solar wind rushed outward from the sun, carrying charged particles and magnetic fields. But when it met the interstellar medium, the thin gas and dust that fills the galaxy, it could not simply flow forever. Instead, it slowed, compressed, and in some regions seemed to form a brightening, as though invisible flames danced at the border. Instruments detected higher levels of energetic particles, a sign that something was blocking or reflecting them. Some scientists began to call it a wall of fire, though others preferred gentler terms like boundary layer or outer sheath. The surprise of this discovery was not only that there was a wall-like region, but that it was sharper and more energetic than models had predicted. For decades, computer simulations had tried to picture what would happen when the solar wind met the interstellar medium. Many thought the transition would stretch across many billions of miles, a long zone of mixing and turbulence. But the data from Voyager suggested that the changes were more abrupt, as if the spacecraft had pressed its hand against something more solid than expected. The plasma density rose quickly, the magnetic fields bent more sharply, cosmic rays that usually streamed in from distant galaxies were partly deflected, then partly allowed through. It was as if the heliosphere, which had always been imagined as a soap bubble drifting in space, actually had a thicker and harder skin than previously believed. The human imagination found it easy to describe this in dramatic language. A wall of fire, a glowing edge, a burning barrier, such words captured the excitement of the discovery, even if the actual reality was one of invisible forces and unseen particles. For the spacecraft themselves, drifting in the cold silence billions of miles from Earth, the discovery was not marked by fireworks or bright lights, but by subtle changes in the readings of sensors. A graph line on a scientist's computer screen would suddenly spike or flatten. A stream of data would change its rhythm. Hours later, when those signals travelled across the immense distance and finally reached Earth, teams of researchers would lean in and realise they were looking at something never before recorded by human hands. Here were probes that had launched when Jimmy Carter was President of the United States, when people listened to music on cassette tapes, when the internet was still a dream, and yet decades later they were sending back discoveries that forced new theories. The idea that the sun is surrounded by a kind of shield, with a boundary that is sharper than expected, meant that the very way the solar system interacts with the galaxy had to be reconsidered. For example, the heliosphere helps protect Earth and the other planets from cosmic rays, those high-energy particles that fly in from exploding stars. If the shield is stronger or weaker than thought, it changes the amount of cosmic radiation that reaches Earth. Over millions of years, that might even affect climate, evolution, and the history of life. The wall-like discovery also sparked ideas about how the galaxy's environment shapes each star system. If our sun's bubble has such a border, then other stars may also blow their own bubbles with their winds. Around each of them there might be similar walls, where their winds meet the interstellar medium. Voyager's discovery was not just about our own system, but about a universal process, repeated billions of times across the galaxy. The data became a window into the relationship between stars and the spaces between them. Voyager 2, which crossed into interstellar space in 2018, also detected changes that seemed to confirm and expand on Voyager 1's earlier findings. Its instruments, still working more than 40 years after launch, sensed a sudden increase in plasma density, a sign that the spacecraft had left the freer-flowing solar wind behind and entered the more crowded interstellar environment. The reading suggested again that the boundary was sharper than expected. By comparing the data from the two spacecraft, scientists could see that the heliosphere's edge was not smooth and round like a perfect bubble, but more wrinkled and shaped by outside pressures. In some places the wall seemed thicker, in others thinner, depending on how the interstellar medium pressed against it. The mystery deepened because neither spacecraft could see the whole picture. They were just two tiny points moving outward in slightly different directions. To imagine the full shape of the heliosphere, scientists had to combine their limited data with models, much as cartographers once tried to draw whole continents from just a few coastlines visited by explorers. And just like those early maps, the first outlines of the heliosphere's wall were full of uncertainty, speculation, and bold strokes of imagination. But the very existence of a sharper barrier meant that the sun's protective bubble was more dynamic than a simple fading away. It was a battleground of forces, a meeting place between the power of a single star and the endless pressure of the galaxy around it. Even the term wall of fire carried a kind of poetic truth. Though there were no flames in the usual sense, the region was full of energetic particles moving at extraordinary speeds, colliding, bouncing, and heating the plasma. Instruments recorded increases in temperature, in pressure, in magnetic turbulence. In human words, it was as though the spacecraft had brushed the edge of a firestorm, though in the silent vacuum of space there was no sound, no visible light, only the invisible signatures that told of immense energies in play. For a spacecraft built in the 1970s, with computers less powerful than a modern pocket calculator, to be able to sense and report such things across billions of miles was itself astonishing. The story of this discovery spread widely in newspapers, magazines, and documentaries. People loved to imagine the spacecraft crossing an invisible frontier, moving from the familiar domain of the sun into the dark ocean of the galaxy. Some compared it to early sailors leaving the sight of land, moving beyond the horizon into seas unknown. Others compared it to ancient travelers stepping from one kingdom into another, passing through guarded gates. To understand why the discovery was so surprising, it helps to picture how thin and delicate the solar wind is. Near Earth, the solar wind has a density of just a few particles per cubic centimetre, far emptier than any vacuum we can create in laboratories. By the time it reaches the outer solar system, that density is even lower. And yet even this faint breath of the sun has strength, enough to carve out a cavity in the interstellar medium. That cavity, the heliosphere, extends billions of miles, protecting the planets inside. When Voyager's instruments detected the piling up of this wind against something, it meant that even at the edge of near nothingness, there were still boundaries and walls. In the vast emptiness, even the faintest flows mattered. The data from Voyager also hinted at mysteries still unsolved. For example, some measurements showed that the magnetic field outside the heliosphere was not aligned as expected. It suggested that the interstellar medium itself had structures and currents not fully understood. Others wondered whether the wall was not just a simple pile-up of plasma, but involved more exotic physics, such as interactions with cosmic rays, or even the influence of galactic magnetic fields stretching across light years. The spacecraft could not answer all these questions, but by raising them it opened paths for new missions in the future. The image of a wall also stirred imaginations about what lies beyond. The heliosphere is like a cocoon, and to step outside it is to leave the sun's protective womb. Voyager, fragile and tiny, had done what no human creation had ever done: slip beyond that shield and into the raw interstellar winds. The discovery of a boundary made that step even more dramatic. It was not a slow fade, but a threshold crossed. Behind the spacecraft was the domain of the sun. Ahead was the realm between the stars. That contrast gave weight to the discovery, a sense of entering the unknown. Voyager's surprise discovery of the wall near the heliosphere's edge was thus more than a detail of plasma physics. It was a moment that blended science, history, and poetry. It showed how reality often defies prediction, how the universe holds more surprises than the neatest models, and how instruments built decades earlier could still reach out and touch mysteries no one had seen before. When the great spacecraft of NASA, known as Voyager 1 and Voyager 2, were launched into the vastness of the universe, nobody could have fully imagined the strange and extraordinary discoveries they would one day send back to Earth. These twin machines, built with the technology of the 1970s, have continued to move outward for decade after decade, travelling far beyond the familiar orbits of the planets, leaving behind the warm glow of the Sun and heading into darker, colder and more mysterious regions. As they kept moving further, they crossed into areas that no other human-made object had ever reached, and it was there that they stumbled upon something astonishing, something that scientists began to call a wall of fire. This was not a wall in the sense of stone or metal, but rather a blazing invisible barrier made of charged particles and high-energy radiation, a boundary where the influence of the Sun fades away and the greater universe beyond begins. The strange wall of fire was not an imagined concept or a dramatic exaggeration. It was something that instruments on both Voyager spacecraft had recorded as they reached the outer limits of the Sun's domain. It marked the place where the winds of the Sun met the opposing winds of the galaxy itself, a line of conflict where the forces of the solar wind pressed against the interstellar medium. The Sun does not merely shine with light and warmth, it also constantly spits out streams of charged particles known as solar wind, which rush outward in every direction at incredible speeds, filling the space between the planets and creating a giant bubble of influence around our star. This bubble, stretching far beyond even the distant orbit of Pluto, is called the heliosphere, and it is like a protective shield surrounding the solar system. But even this bubble cannot go on forever. At some point, the outward rush of the Sun's wind meets the inward pressure of the winds coming from the rest of the galaxy, and at that point, the two forces balance each other. This is the heliopause, the thin and invisible frontier that divides the solar system from the great interstellar ocean beyond. Scientists long suspected such a boundary must exist, but no one had ever touched it or measured it directly until the Voyager spacecraft arrived. They found that it was not a quiet or gentle boundary but a fiery barrier, a turbulent place full of heat and energy, a storm of particles like a cosmic bonfire burning at the edge of our Sun's reach. NASA's heliophysics program described this boundary in simple terms. The picture they painted was that of a boat pushing through a great river, leaving behind swirling wakes of turbulence. In the same way, the Sun's wind crashes into the interstellar medium, creating shock waves and disturbances, which scientists call a bow shock. The fact that the Voyager probes were able to detect and measure this wall of fire is something close to miraculous. These spacecraft are now the only human-made objects that have ever crossed beyond the heliopause and sent back direct information about what lies outside. Their instruments, though old by the standards of modern technology, are still strong enough to record readings of particles, radiation, and magnetic fields in the space they are travelling through. Thanks to them, humanity now has its first real glimpse of the vast uncharted sea that lies beyond the Sun's influence, a place where the galaxy itself presses against the fragile bubble of our solar system. But the fiery barrier was not the only surprise. As Voyager 1 and Voyager 2 kept moving, they began to measure the invisible structure of magnetic fields in that distant region. The Sun itself has a magnetic field, and so does the galaxy outside. For a long time, scientists wondered what would happen when the two met. Would they collide in chaos? Would the outside magnetic field run in a completely different direction from the inside one? Or would they somehow match up? The expectation was that there would be disorder, that the magnetic field of the galaxy would be completely different from the magnetic field shaped by the Sun. Yet the Voyagers found something far stranger. The magnetic field just beyond the heliopause was not pointing in a wildly different direction, but instead it was aligned almost perfectly with the magnetic field inside the heliosphere. This was a discovery that shocked many researchers. NASA explained it in their reports by saying very clearly that the magnetic field beyond the heliopause runs parallel to the magnetic field within the heliosphere itself. This simple alignment, which may sound like a small technical detail, carries deep meaning for the science of space. It means that the reach of the Sun's magnetic influence extends in ways far more orderly than expected. It suggests that there is a kind of cosmic handshake between the Sun and the galaxy, where the invisible lines of force are not tearing against each other, but instead lying side by side, aligned and connected. This strange and elegant alignment forced scientists to rethink many of their old ideas about how the Sun interacts with its surroundings. Before this discovery, it was often assumed that the Sun's protective bubble was like an isolated island, pressed upon by the wild and uncontrolled ocean of the galaxy. Now it seems that there is a deeper harmony at work, where even the magnetic fields at the boundary match and align in surprising ways. With the combined evidence from both Voyager spacecraft, scientists could now form a more complete picture of the delicate balance at the edge of the solar system. The story of the Voyagers themselves makes this discovery even more breathtaking. Voyager 1 was launched in the year 1977, and Voyager 2 was also launched in that same year, only weeks apart. They were built to last a few years, to explore Jupiter, Saturn, Uranus, and Neptune, and then to keep sending information back as long as their instruments survived. Yet here they are, more than 4 decades later, still alive, still sending faint signals back across billions of kilometers of space. Voyager 1 is now more than 14 billion miles from Earth, and Voyager 2 is not far behind. The fact that these tiny human machines have managed to carry their fragile sensors into the farthest and most unknown part of the solar system and beyond is a triumph of human curiosity and engineering. When they crossed the heliopause, the information they carried showed the boundary not as an empty line, but as a dynamic and fiery frontier. The word fire in this case does not mean flames in the ordinary sense, but rather heat, energy, and radiation. The kind of invisible fire that burns not with light, but with charged particles moving at high speeds. It is a wall of fire because it is the place where the solar wind slows and piles up, creating shocks, turbulence, and heat as it clashes with the interstellar medium. The spacecraft recorded sudden changes in particle density, in temperature, in radiation levels, all of which confirmed that they had left the safety of the heliosphere and entered the harsher environment outside. The idea of a bow shock, like the wave made by a boat in water, helps people understand this region more clearly. Imagine the Sun as a boat moving through the galaxy. The solar wind is like the water pushed outward by the boat's front, and when it collides with the larger river around it, waves form, curling and crashing as they struggle against one another. This is what the Voyagers found, except on a scale so large that it defies human imagination. The bubble of the heliosphere is vast beyond comprehension, stretching billions of kilometers in all directions, and at its edge, the bow shock burns like a cosmic flame. The Voyager's readings also brought attention to how the interstellar medium itself behaves. This medium is not empty, even though it may look like a void. It is filled with thin gases, dust, and cosmic rays that travel across the galaxy. At the heliopause, these materials press inward, meeting the outward push of the solar wind. The collision of the two creates turbulence, like air currents meeting at the edge of a storm. The Voyagers, by crossing this region, gave humans their first touch of that galactic sea, their first sense of what the universe beyond the Sun's bubble feels like. Each measurement they sent back told a story of transition. The density of particles increased sharply as they crossed the heliopause. The strength of the solar wind fell suddenly, while the influence of the galactic winds grew stronger. Radiation levels changed, showing that the protective shield of the heliosphere was no longer keeping out cosmic rays as effectively. The spacecraft themselves felt the difference in every reading they made, and through their instruments humanity too felt the passage from one realm to another. The discovery of the magnetic alignment was perhaps even more mysterious. To find that the magnetic field outside was parallel to the one inside was not what most had expected. If the magnetic fields had been chaotic, it would have confirmed many theories about disorder at the galactic boundary. But instead, the calm alignment hinted at unknown patterns in the way the Sun and the galaxy interact. Scientists debated whether this alignment was just a local phenomenon, something that happened only in the region the Voyagers had passed through, or whether it was a broader truth about the whole boundary. The fact that both Voyager 1 and Voyager 2, travelling in different directions, found the same alignment suggests that it is not just local, but something more general, something woven into the structure of the heliopause itself. The data from the Voyagers thus paints a picture of the solar system as a bubble floating within a greater sea, a bubble whose edges are not smooth and quiet but fiery, turbulent, and yet mysteriously ordered. The wall of fire is both a barrier and a gateway, the place where the sun's influence ends and the galaxy begins. Thanks to these small spacecraft, humanity now knows that the boundary is not just a mathematical concept, but a real and dynamic frontier, alive with heat, shock, and strange alignments of magnetic force. The sun is not only a glowing ball of hot gases that shines in the sky and provides light and warmth, but it is also a restless and active engine of energy and matter. From its outer atmosphere, known as the corona, streams of charged particles are constantly escaping into space. This continuous stream is what scientists call the solar wind. It is not a gentle wind like the breeze felt on Earth, but rather a constant outflow of plasma, a mixture of electrons and protons along with some heavier ions, moving at incredible speeds. These speeds can reach hundreds of kilometers per second, sometimes even more than 1,000 kilometers per second, which means the particles are moving faster than anything a human-made aircraft can achieve. This plasma leaves the sun and expands outward in all directions, filling the space around the sun and pushing against the thinner material that drifts between the stars. The solar wind is important because it carves out a giant bubble around the solar system called the heliosphere. This bubble is not solid, and it is not visible to the naked eye, but it is very real. It is made of the plasma that has flown out from the sun for billions of years. The pressure of this plasma moving outward balances against the pressure of material from outside the solar system, the thin gas and particles that float in the galaxy, known as the interstellar medium. Where these two meet, at the farthest edges of the solar system, strange and turbulent boundaries form. One of these boundaries has been described as resembling a wall of fire because of how energetic and intense it appears when studied with instruments. But this fiery appearance is not made of flames like the fire on Earth. Instead, it is the effect of highly charged particles slamming into each other, slowing down, and creating heated regions of plasma that give off radiation detectable by spacecraft like Voyager 1 and Voyager 2. The solar wind is born deep inside the sun. At the core of the sun, nuclear fusion reactions take place. Hydrogen atoms are squeezed together under immense temperature and pressure, producing helium atoms and releasing enormous amounts of energy in the process. This energy moves outward through the dense layers of the sun until it reaches the outer atmosphere, where temperatures soar to millions of degrees. At such extreme heat, atoms are stripped of their electrons, forming plasma. The magnetic field of the sun, which is twisted and ever-changing, helps to accelerate this plasma and fling it into space. Thus, the solar wind is both a product of the sun's heat and its magnetic field. The solar wind does not travel in a straight uniform way. Because the sun rotates and its magnetic field spirals outward, the solar wind is carried into space in a pattern that looks like a spinning pinwheel or a rotating garden sprinkler. This structure is called the Parker spiral, named after the scientist Eugene Parker who first described it. It means that the solar wind is not only rushing outward, but is also shaped into vast curved arcs. This spiral form affects how the particles spread out into space, and how they interact with planets, and with the boundary at the edge of the solar system. As the solar wind flows away from the sun, it carries with it the sun's magnetic field. This is sometimes called the interplanetary magnetic field. The field is stretched out across billions of kilometers, wrapping around planets and pushing against cosmic rays, which are high-energy particles arriving from distant stars and galaxies. Without the solar wind and its magnetic influence, the Earth and other planets would be bombarded more directly by these dangerous cosmic rays. The solar wind therefore acts like a shield, creating a protective environment inside the heliosphere. But this shield is not perfect. It leaks, it fluctuates, and at its farthest edges it collides with the raw forces of the galaxy outside, forming strange layers of compressed plasma that can be imagined as a fiery frontier. The role of the solar wind in creating this boundary is complex. As it rushes outward, the solar wind starts fast and hot near the sun. By the time it has travelled many billions of kilometres, it has cooled somewhat and spread thin, but it still carries momentum. When it finally begins to encounter the interstellar medium, the particles slow down, pile up, and create turbulence. This is where the heliosphere's boundary forms. It is not a sharp wall, but a series of regions. First, There is the termination shock, where the solar wind suddenly slows down from supersonic speeds to subsonic speeds, much like air slowing down when it passes the nose of an airplane. After that comes the heliosheath, a vast turbulent zone filled with hot chaotic plasma. Beyond this lies the heliopause, which is the final boundary where the solar wind's pressure balances with the pressure from interstellar material. Some theories even suggest there is a further outer layer where hydrogen atoms pile up and glow in ultraviolet light, creating something that can be thought of as a wall-like structure. This is what some observers have poetically called a wall of fire. The word fire is not entirely accurate because fire on Earth involves burning fuel in oxygen, producing flames and light. In space there is almost no oxygen, and what happens is not burning in that sense. Instead, the fiery description comes from the heating and excitation of particles. When the solar wind collides with the interstellar medium, energy is transferred, particles are heated to millions of degrees, and radiation is released. This gives the impression of a glowing, fiery frontier, even though the physics is entirely different from fire in the human sense. The Voyager spacecraft provided much of the knowledge about this. Launched in the late 1970s, these spacecraft have been travelling outward for nearly half a century. Voyager 1 crossed the termination shock in the year 2004, and later crossed the heliopause in the year 2012. Voyager 2 crossed the termination shock in the year 2007, and reached the heliopause in the year 2018. Their instruments measured changes in particle density, temperature, magnetic fields, and radiation as they passed through these regions. They detected sudden rises in plasma density, changes in the flow of charged particles, and shifts in cosmic ray intensity. All of these observations showed that the solar wind plays the main role in shaping this enormous and fiery-looking boundary. One of the most important aspects of the solar wind is that it is not constant. The Sun goes through cycles of activity roughly every 11 years. During the maximum part of the cycle, the Sun produces more sunspots, more solar flares, and more coronal mass ejections. These events release bursts of plasma and magnetic fields into space, temporarily increasing the intensity of the solar wind. During the quieter minimum part of the cycle, the solar wind is less intense. This rhythm means that the shape and strength of the heliosphere are always changing, swelling outward during active times and shrinking slightly during quieter times. This breathing motion of the heliosphere influences how the boundary appears and how fiery or turbulent it seems when spacecraft encounter it. On Earth, the solar wind is usually not noticed directly because our planet has its own magnetic field, the magnetosphere, which deflects most of the charged particles. But sometimes when the solar wind is strong, it pushes against the Earth's magnetic field and causes geomagnetic storms. These storms can create beautiful auroras, the northern and southern lights, but they can also disturb satellites, power grids, and communication systems. This shows that the solar wind is powerful even close to Earth, so one can imagine how much larger its role is in creating the outer boundary far beyond the planets. The physics of the solar wind can be described with plasma physics. Plasma is often called the fourth state of matter, different from solids, liquids, and gases. In plasma, electrons and ions move freely, and this makes plasma highly responsive to magnetic and electric fields. The solar wind plasma expands outward because the corona is so hot that the Sun's gravity cannot hold on to all the particles. Parker's solar wind model showed that at some distance from the Sun, the particles accelerate and keep flowing outward forever. As the plasma flows, it carries energy and momentum, and this shapes everything in its path. At the outer edges, where the solar wind slows and collides with interstellar gas, shock waves are formed. These shocks are similar in concept to the sonic booms produced when jets fly faster than sound. In space, these plasma shocks heat particles, accelerate cosmic rays, and create turbulent fields. The result is a zone of violent particle interactions, which gives rise to radiation that spacecraft can detect. To instruments, it looks like a wall of intense energy, like fire. In reality, it is the Sun's own breath colliding with the breath of the galaxy. One can also think of the heliosphere as a shielded bubble in a cosmic ocean. Inside this bubble, the solar wind dominates. Outside, the interstellar medium dominates. The boundary is where the two oceans meet, churning and boiling. The fiery look comes from the fact that plasma at millions of degrees behaves in ways that resemble flames, releasing energy across many wavelengths, including ultraviolet and X-ray light. To scientists, this is an invaluable laboratory for studying plasma physics on a grand scale, because these processes cannot be recreated easily on Earth. Even though the solar wind is very thin, with only a few particles per cubic centimetre, it has a huge impact because it extends so far. By the time it reaches the termination shock, billions of kilometres from the Sun, it still carries enough energy to push against the interstellar medium. The heliosphere is estimated to extend more than 100 astronomical units from the Sun in some directions. 1 astronomical unit is the average distance from Earth to the Sun, about 150 million kilometres. That means the solar wind creates a protective bubble that is billions and billions of kilometres wide. Without this outflow, the solar system would be exposed directly to interstellar particles, which might have influenced the formation of planets and the possibility of life. The role of the solar wind also extends to how cosmic rays are filtered. Galactic cosmic rays are charged particles travelling at nearly the speed of light, produced by supernova explosions and other extreme cosmic events. These rays are dangerous because they can damage DNA, electronics and spacecraft. The solar wind and the heliosphere reduce the amount of cosmic rays that reach the inner solar system. When Voyager crossed the heliopause, it measured a sharp increase in cosmic rays, showing how effective the solar wind is at shielding the inside of the bubble. This shielding effect is one of the most important contributions of the solar wind to life on Earth and to the fiery-looking boundary beyond. The science of the solar wind is still being explored. New missions, like the Parker Solar Probe launched in the year 2018, are flying closer to the Sun than any spacecraft before, diving into the corona to study how the solar wind is launched and accelerated. Other missions, like the Interstellar Mapping and Acceleration Probe planned for the near future, will study the edges of the heliosphere in greater detail. These studies will reveal more about how the solar wind contributes to the appearance of the outer boundary and why it looks fiery and turbulent when measured. In the grand scale of astrophysics, the solar wind is not unique. Other stars also produce stellar winds, and their winds also carve out bubbles in the interstellar medium. Some of these bubbles overlap, forming large cavities in the galaxy. By studying our own solar wind and heliosphere, scientists learn about the processes happening around other stars as well. This makes the study of the solar wind not just a matter of understanding the Sun, but of understanding the galaxy and the universe. The space between the stars is not empty in the way we often imagine emptiness. It is filled with a thin, ghostly sea of charged particles, magnetic fields and radiation that move and push and twist in ways that can change the path of a tiny, fast particle coming from far away. Galactic cosmic rays are those tiny, very energetic particles that come from outside our own star system, born in the explosions of old stars, in the winds from young, massive stars, in the shock fronts of supernova remnants, and possibly from other violent sites across the galaxy. These particles travel almost at the speed of light, and when they reach the neighbourhood of our Sun, they must cross a region shaped by the Sun's continuous outflow of charged gas known as the solar wind. The interaction between that solar wind bubble and the surrounding interstellar medium creates a complex boundary region that can act like a partial wall for cosmic rays, bending some, slowing down others, and changing their intensities and directions in ways that look to instruments like a blockage or a deflection. Saying the boundary blocks or redirects cosmic rays is shorthand for a set of physical processes that depend on particle energy, magnetic field geometry, plasma turbulence, and the flow of material, all of which work together to make the number and direction of particles measured inside the bubble different from what exists outside it. At its simplest, a charged particle moving through space is guided by magnetic fields and by random scattering from irregularities in those fields. If there were no magnetic field at all, cosmic ray particles would fly in straight lines, and whether they reached the inner parts of the solar system would depend only on geometry and whether anything collides with them. But cosmic rays are charged, and charged particles follow curved paths in magnetic fields. The Sun's magnetic field, carried outward by the solar wind, forms a large rotating spiral structure and a region of disturbed magnetic geometry. Outside of that region, the magnetic field of the local interstellar medium has its own orientation. Where these two magnetic environments meet, field lines can bend, drape, and compress. That bending changes the effective routes cosmic rays can take. Particles with low rigidity meaning roughly how hard it is to bend their path, which depends on momentum divided by charge, are more strongly deflected than high rigidity particles. So the wall appears more effective for lower energy cosmic rays and less effective for the highest energies, which can more readily plough through bent magnetic fields. The result is an energy-dependent filtering. The boundary acts like a sieve, letting through more of the highest energy particles and fewer of the lower energy ones, which produces changes in the measured energy spectrum on the inside of the heliospheric bubble versus the outside. Magnetic field geometry alone, however, is not the whole story. The plasma that flows from the Sun forms different regions as it meets the pressure of the interstellar medium. As the solar wind expands and slows, it can form a termination shock, a turbulent inner layer called the heliosheath, and then finally the heliopause, the outermost surface where the solar wind's outward pressure balances the interstellar pressure. These regions are not calm. They contain turbulent eddies, waves, and irregularities that can scatter charged particles. Scattering means that a particle's direction of motion relative to the local magnetic field, its pitch angle, can change randomly when it encounters magnetic turbulence or wave activity. That scattering turns a simple straight trajectory into a zigzag path, making the particle's effective progress slower and more diffusive. In regions where turbulence is strong and the magnetic field lines are tangled, cosmic rays find it harder to pass straight through. They may instead spend more time trapped, bouncing between scattering centers, or they may drift along preferred directions dictated by field gradients and curvature. Over macroscopic distances, this behavior can look like a barrier that slows the flow of particles, reducing the flux of certain energies on the other side. One important mechanism to think about is diffusion. In the language of particles and fields, diffusion describes how particles spread from regions of high concentration to regions of lower concentration when their paths are randomized by scattering. In the heliospheric boundary region, the diffusion coefficient, a quantity that measures how easily particles diffuse, depends on particle rigidity and on the level and scale of magnetic turbulence. Models of cosmic ray transport often start with a diffusion-convection equation that balances diffusion, large-scale flows like the solar wind, and processes that add or remove particles such as sources, sinks, and energy changes. When the diffusion coefficient drops in a boundary layer because turbulence or magnetic compression increases, the effective resistance to particle transport grows. That produces a gradient in the particle density across the layer, which observationally looks like a sudden decrease or shadowing of cosmic rays inside the bubble relative to outside. In other words, as cosmic rays try to cross into the heliosphere, they face a region where scattering increases their residence time and lowers their chance of efficient passage, so fewer particles make it across per unit time. Connected to diffusion is the idea of magnetic mirroring and field line draping. Imagine magnetic field lines as invisible rails in space. If field lines compress or change orientation, a particle moving along those rails can find regions where the magnetic field strength increases. Because of a particle's magnetic moment, a conserved quantity when the field changes slowly compared to the particle's gyration, the particle can be reflected from regions of stronger field back toward weaker field. This mirror effect can trap particles or reflect them back to their source region, acting like a magnetic mirror that prevents some fraction of particles from penetrating further. At the heliopause, the interstellar magnetic field can be draped around the heliosphere like fabric blown back by a wind, which creates regions of enhanced field strength on the flanks and nose. In those enhanced field zones, the mirror effect becomes more pronounced and contributes to the apparent blocking or deflection of cosmic rays. The detailed shape of the draped field depends on the angle between the interstellar field and the incoming solar wind, as well as on the local plasma conditions. But wherever the field compresses, the mirror effect can act as a selective reflector for certain pitch angles and energies. There is also the role of particle drifts. Charged particles in non-uniform magnetic fields experience drift motions that depend on the direction of the field gradient and the particle's charge and energy. Gradient drift and curvature drift move particles across field lines in systematic ways, and when the boundary region has strong gradients or curvature in the field structure, those drift motions can steer particles preferentially along certain paths instead of letting them pass directly through. drift effects are particularly important for particles in the rigidity range, where they are neither tightly bound to field lines nor so energetic that they ignore field structure. In that intermediate regime, drifts can dominate transport and lead to anisotropies in the arrival directions of cosmic rays. The interaction between solar cycle variations and cosmic ray modulation further complicates the picture. The Sun's magnetic field flips polarity roughly every 11 years, and the strength and turbulence levels of the solar wind vary over this cycle. When the Sun is more active, enhanced solar wind structures, coronal mass ejections, and stronger turbulence can lead to stronger scattering and lower diffusion coefficients near the heliosphere, producing a deeper modulation of cosmic rays inside the bubble. During quieter solar times, the heliosphere becomes more transparent to particles at certain energies. Because the heliosphere is dynamic, the apparent blocking effect of its outer boundary changes with time, producing time-varying cosmic ray fluxes at different locations. When spacecraft like the Voyagers move outward, they sample a changing environment, and their instruments record shifts in particle intensities that track both spatial structure and temporal evolution. So what looks like a permanent wall may in fact be a time-dependent dynamic layer that evolves with solar activity and local interstellar conditions. Another piece of this puzzle is the population of pickup ions and locally accelerated particles inside the boundary region. Neutral atoms from the interstellar medium can enter the heliosphere uncharged and later become ionized by solar ultraviolet light or charge exchange. Once ionized, they are grabbed by the solar wind's electromagnetic fields and accelerated up to the local flow speed, becoming pickup ions. These pickup ions add mass, energy, and instability drivers to the plasma, and they can generate waves and turbulence that modify how cosmic rays scatter. In regions where pickup ions are abundant, they can serve as a source of micro-instabilities that increase magnetic irregularities, thereby lowering diffusion coefficients for galactic cosmic rays and amplifying the filtering effect. In addition, shock-like features and turbulence within the heliosheath can sometimes accelerate particles locally through processes akin to diffusive shock acceleration, producing energetic particle populations that mix with incoming galactic cosmic rays and change the net spectrum measured. Those locally produced particles can complicate interpretation, because an instrument may see a change in total energetic particle counts, but must tease apart what fraction is external galactic flux and what fraction is local acceleration. Observationally, scientists look at both intensity and directional information to infer how the boundary interacts with cosmic rays. If the boundary simply absorbed particles, one might see a sharp drop and no directional preference. Instead, the boundary often produces anisotropies, sudden increases in magnetic field strength, and shifts in the composition and spectral slopes of the measured particles. For example, if a spacecraft moves outward and encounters a compressed magnetic region, instruments might record a drop in particle intensity at intermediate energies, a change in the angular distribution of incoming particles, and simultaneously an increase in field strength and plasma density. Those simultaneous signatures point to a picture where magnetic and plasma structures create effective barriers, not absolute walls. Instruments on long-duration probes have recorded abrupt changes that can look like walls on the scale of a few astronomical units, but when examined with care they reveal a layered structure. Regions of enhanced field and turbulence, zones of compressed plasma, and pockets where drifts and mirrors reshape the flow of particles. The language of scattering theory gives another angle to explain how the wall seems to work. Cosmic ray scattering is often treated in terms of resonant interactions between particles and magnetic field fluctuations, whose wavelengths match the particle's gyroradius. When turbulence has a spectrum of scales, particles of different gyroradii will interact with different parts of that spectrum. If the boundary layer concentrates power at scales that resonate with a particular energy range, scattering increases selectively for those particles. The result is a selective reduction in diffusion and an energy-dependent attenuation that makes the boundary look more opaque at certain energies. Since particle gyroradius scales with rigidity, this resonant interaction produces the familiar rigidity dependence of cosmic ray modulation. Lower rigidity particles are scattered more and less likely to get through, while higher rigidity particles with larger gyroradii are less affected by the same turbulent spectrum. Transport is also influenced by large-scale flows. The solar wind itself is an outward convective flow that tends to carry particles away from the inner system. When that flow meets a boundary layer, The competition between convective outward transport and diffusive inward transport determines whether particles can penetrate. If outward convection dominates locally, the net inward flux of cosmic rays is reduced, producing the impression of a barrier. Conversely, if diffusion is strong compared to convection, particles leak in more easily. The balance between convection and diffusion varies with location and time, so some parts of the boundary can be more permeable than others. This balance is often described in terms of a Pecklet-like number for cosmic rays, comparing advective to diffusive timescales, and where the advective effect is strong, the cosmic ray intensity inside can be suppressed. Wave phenomena and kinetic scale physics add further richness. The boundary can host wave modes like alphonic turbulence, mirror mode structures, and kinetic instabilities driven by temperature anisotropies or differential flows. These waves can scatter particles pitch angle-wise, and can even trap particles in coherent structures. Mirror modes create magnetic bottle-like regions where a particle can become temporarily confined. Their presence in a boundary layer increases residence time and reduces net transmission. Small-scale electric fields and the presence of plasma sheets with variable charge separation can produce perpendicular heating or drift motions that change particle trajectories. Even subtle changes in plasma beta, the ratio of kinetic to magnetic pressure, change which wave modes are favoured, and therefore which scattering processes become important. All of this makes the boundary function not as a simple solid sheet, but as a multi-scale filter built from a hierarchy of physical processes. Computational models and analytic theories try to capture these processes with a mix of magnetohydrodynamic (MHD) descriptions for the large-scale flow and turbulence, and kinetic treatments for the particles themselves. Single fluid MHD can predict where the heliopause may sit and how the interstellar field drapes, but kinetic effects control the scattering of particles at the small scales. Hybrid models, which treat ions kinetically and electrons as a fluid, and full particle-in-cell simulations which resolve kinetic scales, are used to probe how microphysics builds up to macroscopic barriers. Those models show that even modest field compressions combined with the right turbulence spectra can produce noticeable modulation of cosmic rays. Simulations also reveal that time-dependent phenomena, for instance, a burst of turbulence generated by a shock passing through the heliosheath, can temporarily tighten the barrier, reducing fluxes for months or years before relaxing again. This matches observations where cosmic ray intensities show transient decreases associated with solar events, propagating outward and reaching the boundary. When thinking about the term block, it is useful to consider the concept of optical depth adapted to energetic particles. In radiative transfer, optical depth measures the likelihood that a photon is absorbed or scattered before it escapes a medium. For cosmic rays, one can imagine an analogous quantity that measures the cumulative scattering and reflection probability across the boundary. If the integrated scattering probability is high for certain energies, those energies will be effectively suppressed inside, giving the impression of a high optical depth. But unlike a hard wall, the optical depth varies smoothly with energy, angle, and time. So the wall is more like a region of high optical depth for specific particle populations. The interstellar environment also matters. The local interstellar magnetic field orientation, its turbulence level, and the density and temperature of the surrounding plasma all influence how the heliosphere's outer surface forms. If the interstellar field is strong and oriented in a way that causes heavy draping, the barrier effect is stronger. If the interstellar medium is more gentle, the boundary is more porous. Moreover, the relative motion between the Sun and the local interstellar medium creates a nose-tail asymmetry. The front side facing the incoming interstellar flow experiences stronger compression, and therefore may be a stronger reflector, while the tail region can be more open. This asymmetry produces anisotropic filtering of cosmic rays depending on their direction of approach, which is why directional measurements are so valuable for diagnosing the boundary's behaviour. Finally, observational uncertainty and instrument response must be kept in mind. Instruments detect count rates of particles within a range of energies. Sudden changes may reflect not only true spatial variations, but also changes in particle composition or local acceleration. Teasing apart whether a drop in measured counts is because of blocking, redirection, or replacement by locally produced particles demands careful multi-instrument analysis and cross-comparison with fields and plasma data. That is why missions that carry both particle detectors and magnetometers are so powerful. Combined datasets allow researchers to match particle behavior with the magnetic and plasma context, revealing whether a decrease in cosmic rays correlates with a compressed field or with a burst of local acceleration. Taken together, these ideas show why the heliospheric boundary can act like a partial wall for galactic cosmic rays. It is not a literal solid surface that stops everything, but rather a layered, dynamic and energy-dependent filter built from magnetic geometry, turbulence-driven scattering, convective flows, drift motions, mirror effects, local plasma populations, and time-varying solar and interstellar conditions. The wall-like behavior emerges when many of these effects align to reduce the inward flux of particles in a given energy band, producing sharp gradients and directional signatures that look to an observer like a boundary that blocks or redirects cosmic rays from deep space. Observations showing energy-dependent attenuation, anisotropies, and correlated changes in magnetic and plasma properties provide the empirical basis for this interpretation, while theoretical models and numerical simulations explain how the underlying physics, diffusion, drift, mirroring, local acceleration and convection, combine to make the boundary behave as it does. All of these processes are active at once, and their balance changes with time and location, so the apparent wall is best thought of as a living, fluctuating interface, rather than a permanent, unchanging barrier. The edge of the solar system is not like the quiet emptiness many once imagined. It is instead a place of strange forces, unexpected energies, and puzzling changes in the behavior of matter. When the spacecraft known as Voyager 1 and Voyager 2, launched in the year 1977, began approaching this distant boundary region, scientists were prepared to witness something unusual, but what they actually found was far more complex. The plasma that fills the space at the very edge of the solar system turned out to be hotter and denser than theories and models had predicted. This was not a simple deviation, but a large difference between expectation and observation, which made researchers realize that the rules governing this region might involve interactions more subtle and more powerful than they had fully grasped before. Plasma, in the simplest sense, is gas that has been heated so much that its atoms are no longer whole. The electrons are stripped away from their parent nuclei, leaving a sea of charged particles, some positive and some negative, swirling and colliding under the influence of electric and magnetic forces. This plasma flows outward from the Sun in a steady stream called the solar wind, carrying with it heat, energy, and the magnetic field of the Sun. Near Earth, this wind can be measured and studied with great accuracy, but at the farthest limits, billions of kilometers away, the solar wind meets the material that fills interstellar space, and it is here that something unexpected happens. The simple models once suggested that the plasma would slow down, spread out, and lose energy, becoming cooler and thinner as it encountered the resistance of interstellar matter. Instead, Voyager found that the plasma was compressed, energized, and made hotter than expected. The reason behind this strange heating is not yet completely solved. One idea is that as the solar wind pushes against the material of interstellar space, enormous shock waves form. These shocks are like giant cosmic versions of the shock wave in front of a supersonic jet. When charged particles are forced across such a boundary, their random motions increase, and the energy that once was mainly in the flow is converted into heat. But this does not explain everything, because the density of the plasma is also greater than what models had suggested. Some of the energy that was supposed to leak away seems instead to be trapped, raising the pressure and heat inside the boundary region. Another idea is that magnetic fields play a larger role than had been expected. The Sun's magnetic field, carried outward by the solar wind, is twisted into a spiral by the rotation of the Sun, a shape often called the Parker spiral, after the scientist who first described it. At the edges of the heliosphere, this spiral field may pile up, fold, reconnect, and form tangled regions where magnetic energy is explosively converted into heat. Magnetic reconnection is a process observed near Earth as well, where it causes bursts of auroras and geomagnetic storms, but at the boundary of the solar system it may be happening on a far grander scale, feeding extra heat into the plasma. If magnetic reconnection is more frequent there than once thought, this could be one source of the hotter than expected plasma. Density also matters. Voyager instruments revealed that the number of particles in this region was far higher than anticipated. A dense plasma resists the outward push of the solar wind more strongly, so instead of flowing smoothly, the solar wind may be compressed like water building behind a dam. This compression would increase both density and temperature, because the energy has fewer places to go, and thus is concentrated in a smaller space. It is like pressing down on a gas with a piston, making it hotter and denser at the same time. But what could cause this extra density? One possibility is that the solar wind sweeps up material from interstellar space and carries it along for a while before it can escape. These neutral atoms of hydrogen and helium from outside the solar system can become ionized by collisions or by solar radiation, and once they turn into charged particles, they join the plasma. This extra load of particles may help to explain the unexpected density. There is also evidence that turbulence plays a role. Instead of being a smooth flow, the plasma at the edge seems to swirl and churn, forming eddies and vortices like a boiling liquid. Turbulence can mix energy into smaller and smaller scales, raising local temperatures. Voyager detected fluctuations in plasma properties that hinted at such turbulence, which would provide another way of heating the plasma. In fluid dynamics and plasma physics, turbulence is known to be one of the hardest problems, because it involves nonlinear processes and cascading motions that defy easy prediction. In the heliosheath, the outer layer of the solar wind just before interstellar space, turbulence may be strong enough to account for the unexpected heat. Shock waves, magnetic reconnection, turbulence, and particle pickup from interstellar matter are not isolated processes, but may all be happening together. This means the boundary of the solar system is not a simple wall but a dynamic changing region where many kinds of physical processes interact. The hotter plasma observed by Voyager is a sign that energy is being transformed and redistributed in ways that are still being unraveled. Scientists build computer models of this region, trying to include all these processes, but it remains difficult because the distances are so vast, the scale so immense, and the physics so interconnected. Voyager 1 crossed into interstellar space in the year 2012, and Voyager 2 followed in the year 2018. Both probes carried instruments that could sense charged particles, magnetic fields, and plasma waves. The direct plasma detector on Voyager 1 stopped working years earlier, but even without it, scientists could measure plasma density by listening to plasma oscillations, which are natural vibrations that occur in charged gases. When energetic electrons pass through plasma, they excite oscillations, and from their frequency the density can be calculated. In the year 2013, Voyager 1 detected such plasma oscillations triggered by a solar outburst that had travelled outward for more than a year before reaching the boundary. The measured frequency revealed a plasma density much higher than expected, confirming that this outer region is indeed denser and hotter than the old models predicted. Why would this matter so much? Because the boundary is the frontier where our solar system interacts with the galaxy beyond. Understanding it means learning how our protective bubble, the heliosphere, defends us from galactic cosmic rays, how energy from the sun is spread into space, and how other stars might shape their own surrounding bubbles. If the plasma is hotter and denser, it changes how cosmic rays filter in, how magnetic fields are carried outward, and how long the solar wind maintains its pressure before giving way to the interstellar medium. These details are not small. They determine the shape and size of the heliosphere itself. The heliosphere can be imagined as a great bubble blown by the sun. Inside it, solar particles dominate, while outside, interstellar particles dominate. The edge is called the heliopause, and just before it lies the heliosheath. In this heliosheath is where the heating and compression seem strongest. The solar wind slows down after passing through the termination shock, a point discovered by Voyager 2 in the year 2007. At that shock, the supersonic solar wind suddenly becomes subsonic, losing speed but gaining heat. It was already expected that this would warm the plasma, but not to the levels actually recorded. Something more was at work, and the discoveries of Voyager forced scientists to rethink their models. One remarkable detail is how these conditions may vary with time. The solar wind is not constant. It changes with the solar cycle, which is about 11 years long. During times of high solar activity, the solar wind is stronger and more turbulent, which could lead to more heating at the edge. During times of low activity, the wind is weaker, and the balance of forces at the boundary shifts. This means the temperature and density at the edge may not be fixed but may rise and fall with the rhythms of the Sun. Voyager happened to measure at certain phases of this cycle, and later spacecraft such as the planned Interstellar probe mission may reveal how these conditions change more completely. From the perspective of plasma physics, the heating at the boundary can also be thought of in terms of kinetic and thermal energy. The solar wind starts with a lot of kinetic energy, moving outward at hundreds of kilometers per second. When it collides with the resistance of interstellar material, much of this motion is converted into random thermal motion. Random motion is what defines heat, so this conversion naturally makes the plasma hotter. If the resistance is stronger than expected, then more kinetic energy gets turned into heat, raising the temperature beyond predictions. The interstellar medium itself is not empty. It contains neutral hydrogen atoms, dust, cosmic rays, and magnetic fields. The interaction between the solar wind and this medium is what defines the structure of the heliosphere. The fact that plasma at the edge is denser and hotter suggests that the interstellar medium may be denser too, or that the interaction is more effective at trapping energy than was once thought. Scientists study the ultraviolet light from distant stars to measure how much hydrogen lies between them and Earth, and these observations help refine estimates of the density of the interstellar medium. Combining these with the Voyager data gives a better picture, but it is still a mystery how exactly the energy balance is maintained. Some researchers have proposed that wave-particle interactions are part of the puzzle. In plasma, particles do not just move randomly, they can resonate with waves in the magnetic field, exchanging energy. These plasma waves can scatter particles, accelerating some and slowing others, redistributing energy in complex ways. Voyager recorded many kinds of plasma waves at the edge, and their role in heating is still being explored. Wave-particle interactions are known to be efficient at transferring energy in other environments, such as Earth's magnetosphere, so it is reasonable to think they are active here as well. The heat measured at the boundary may also depend on anisotropies, meaning that the plasma does not behave the same in every direction. If some particles move faster along magnetic field lines than across them, this can lead to instabilities that generate extra waves and turbulence. These instabilities can heat plasma locally, again raising the overall temperature beyond simple predictions. The Voyager data hinted at such anisotropies, though the instruments were not designed to capture every detail. Because of these complexities, the heliopause is now seen not as a quiet dividing line, but as a highly active region where many processes add together. The hotter and denser plasma is a symptom of this activity. By continuing to analyze the Voyager data and by planning future missions, scientists hope to learn how the Sun's energy and the galaxy's material meet and transform at this grand boundary. Even the word hot in this context needs to be understood carefully. In space, temperature does not mean the same thing as it does in air on Earth. A plasma may be extremely hot in terms of the energy of individual particles, with temperatures of hundreds of thousands or even millions of degrees, but because the density is so low, it would not feel hot to a human hand. There are simply too few particles to transfer much heat. At the heliospheric boundary, the plasma is hotter than expected in this technical sense, meaning the average energy per particle is greater. This is a key distinction that helps avoid confusion when talking about cosmic temperatures. The density, too, has a different meaning in space. Compared to Earth's atmosphere, which has trillions of particles per cubic centimetre, the plasma at the edge of the solar system may have only a fraction of a particle per cubic centimetre. Yet this is still higher than the models predicted, and in space physics such small differences matter greatly. An increase from 1/10 of a particle per cubic centimetre to 5/10, for example, is a large factor, and it alters how magnetic fields, shock waves, and cosmic rays behave. The hotter and denser plasma is not merely a curiosity, but a window into the physics of astrophysical boundaries in general. Every star creates a bubble like the heliosphere, and the edges of these bubbles may all have similar processes. By studying our own in detail, we can learn about how stars interact with the galaxy, how they shield their planets from cosmic rays, and how matter and energy are exchanged between stellar systems and interstellar space. The Voyager spacecraft, though small and decades old, have given us the first direct data on this frontier, and those data have already challenged long-held assumptions. The theories that seemed sufficient when applied to gases did not fully apply here. Plasma can store and release magnetic energy, form shock structures that accelerate particles to near the speed of light, and support waves of many kinds. The hotter and denser plasma at the edge is not simply a matter of extra heat, but a sign that plasma physics itself must be considered in all its complexity. As the probes continue their journey into deeper interstellar space, they will keep sending signals back to Earth. Though weaker with each passing year, their power supplies are fading, and eventually they will go silent, but the data already returned will continue to be studied. Future missions with modern instruments may one day confirm and extend the findings, showing with greater clarity why the plasma at the edge of the solar system is hotter and denser than scientists once believed. Plasma is often called the fourth state of matter, but this name hardly captures its richness. Unlike solids, liquids, and gases, which are neutral collections of atoms and molecules, plasma is made of free electrons and ions, each carrying an electric charge. Because of this, plasma does not simply obey the rules of ordinary gases. Instead, it is guided by the interplay of electric and magnetic fields, which can stretch across vast distances. At the edge of the solar system, plasma fills the heliosheath, and here the properties of charged particles become especially important. The hotter and denser plasma measured by Voyager shows that the energy balance is different than what neutral gas models once suggested. To understand this difference, one must dive deeply into plasma physics, where shocks, turbulence, wave-particle interactions and magnetic reconnection shape the behavior of matter. When the solar wind streams outward from the Sun, it moves at hundreds of kilometers per second, often around 400 to 800 kilometers per second near Earth. This makes it supersonic relative to the local plasma environment. In fluid mechanics, when a supersonic flow encounters resistance, it produces a shock wave, a sudden compression that converts kinetic energy into heat. In space plasmas, shocks are more complicated than in air, because they involve magnetic fields and charged particles. These are called collisionless shocks, since the particles do not collide like molecules in air, but instead are deflected and slowed by electromagnetic forces. The termination shock of the solar wind, discovered by Voyager 2 in the year 2007, is one such collisionless shock. Instead of simply slowing down the wind, it energizes particles, scatters them, and generates waves. At this point, part of the ordered flow of the solar wind is turned into random thermal motion, heating the plasma. Yet even taking this into account, the temperatures measured beyond were higher than expected, showing that additional processes continue to heat the plasma as it travels outward into the heliosheath. These shocks are also capable of accelerating particles to cosmic ray energies. As particles bounce back and forth across the shock front, they gain energy in a process known as diffusive shock acceleration. This mechanism is thought to be one of the main ways cosmic rays are produced in the universe, especially in supernova remnants. The fact that a similar process is occurring at the edge of the solar system shows a parallel between local plasma physics and galactic astrophysics. Just as shocks in dying stars produce high-energy cosmic rays, the shock of the solar wind termination heats and accelerates particles, leaving its signature in the higher-than-expected temperatures recorded by Voyager. The solar cycle influences this picture further. The Sun's magnetic field flips polarity every 11 years, driving cycles of solar activity marked by sunspots, flares, and coronal mass ejections. During times of solar maximum, the solar wind is more turbulent, carrying with it stronger magnetic fields and more frequent bursts of energy. When these bursts propagate outward, they steepen into shocks and interact with the boundary regions. This can pump additional energy into the plasma at the edge, raising both temperature and density. Voyager observed plasma oscillations that were triggered by solar outbursts launched more than a year earlier, showing that the edge is directly influenced by the state of the Sun many billions of kilometers away. At solar minimum, when the Sun is calmer, the conditions at the edge may be different, but Voyager's data reveal that even during quieter times, the plasma remains hotter than expected, suggesting that continuous processes such as turbulence and reconnection sustain the heat. Turbulence in plasma is not like the turbulence of air in the atmosphere. In a plasma, turbulence involves both fluid motions and fluctuations in magnetic and electric fields. Energy injected at large scales cascades down to smaller and smaller scales until it is dissipated into particle heating. The heliosheath, being a region of slowed and compressed solar wind, is expected to be turbulent, and Voyager detected variations consistent with this. Such turbulence can heat the plasma efficiently, explaining why temperatures remain higher than models based on simple compression would predict. In plasma turbulence, wave-particle interactions play a central role. Particles can resonate with waves in the magnetic field, gaining or losing energy. Alphen waves, a type of wave that travels along magnetic field lines, are particularly important. When particles resonate with alphen waves, their random motions increase, and this contributes to heating. At the edge of the solar system, such resonances may be widespread, making the plasma hotter and denser than expected. Magnetic reconnection is another process that could explain the excess heat. The Sun's magnetic field, carried outward by the solar wind, is twisted into a spiral. At the heliosheath, different regions of this field can collide and reconnect, releasing stored magnetic energy explosively. On Earth, reconnection is seen in the magnetotail, where it powers auroras and geomagnetic storms. At the heliospheric boundary, reconnection may happen on a much larger scale, heating plasma across vast distances. Each reconnection event converts magnetic energy into particle energy, raising both the temperature and the density. Since Voyager detected irregular fluctuations in magnetic fields, reconnection seems a likely contributor to the hotter-than-expected plasma. The denser plasma is also explained by particle pickup. Interstellar space contains neutral atoms of hydrogen and helium that drift into the heliosphere. When these atoms encounter solar ultraviolet light or charge exchange with solar wind ions, they become ionized. Once ionized, they are caught by the solar magnetic field and carried along with the solar wind, becoming part of the plasma. This process increases the number of particles in the heliosheath, raising the density. These pickup ions also carry significant energy, because they are born moving at the speed of the solar wind relative to the Sun. Their presence adds to both the heat and the density, explaining part of the Voyager findings. This mixture of processes means the heliosheath is a laboratory of plasma physics, where many phenomena long studied in theory can be seen at work. For example, in laboratory plasmas on Earth, researchers see evidence of turbulence, reconnection, and wave-particle interactions on small scales. At the heliospheric boundary, the same processes occur, but on scales measured in billions of kilometers. This makes the Voyager data not just a window into the solar system, but also into plasma behavior across the universe. Parallels can be drawn with astrophysical systems such as the bow shocks of other stars. Just as the Sun produces a heliosphere, other stars blow bubbles into the interstellar medium, known as astrospheres. Observations of these distant bubbles, often detected through ultraviolet light absorption, show evidence of heated plasma at their edges as well. By comparing the heliosphere to astrospheres, scientists can test whether the hotter and denser plasma is a universal feature of such boundaries. If so, this would mean that across the galaxy, stars shape their environments in ways similar to what Voyager observed for our Sun. Supernova remnants provide another parallel. When a massive star explodes, it sends out a shock wave into the interstellar medium. At the edge of this expanding shock, plasma is heated and particles are accelerated, producing emissions that astronomers can detect across the spectrum, from radio waves to X-rays. The heating observed at the heliospheric boundary is on a smaller scale, but follows similar principles. In both cases, shock dynamics convert bulk motion into heat, turbulence spreads energy across scales, and magnetic processes release stored energy. This shows that the physics of the heliosheath is connected to some of the most powerful events in the universe. Even galaxy clusters, the largest structures bound by gravity, show parallels. When galaxies collide, or when matter falls into clusters, shocks and turbulence heat the intergalactic plasma, raising its temperature to tens of millions of degrees. X-ray telescopes observe this hot plasma, revealing that the same basic processes — shocks, turbulence, reconnection — govern energy distribution on scales much larger than the heliosphere. Voyager's measurements are thus a small-scale example of universal plasma processes. Returning to the solar cycle, one must consider that the heliosphere itself breathes in and out with the changing activity of the Sun. During strong solar cycles, the heliosphere expands, pushing the boundary outward. During weaker cycles, it contracts. This expansion and contraction change the balance of forces at the edge, altering how heat and density accumulate. The plasma observed by Voyager may reflect the state of the heliosphere during a particular solar cycle phase. If future missions could observe across multiple cycles, scientists could measure how the heating varies with time, testing whether turbulence and reconnection are steady processes or whether they wax and wane with the sun's rhythm. The existence of a hotter and denser plasma also influences how galactic cosmic rays enter the solar system. Cosmic rays are high-energy particles, mostly protons, that travel across the galaxy. The heliosphere acts as a shield, deflecting and slowing them before they reach Earth. A denser and hotter boundary region alters this shielding, perhaps making it more effective at some times and less at others. This has direct consequences for life on Earth and for astronauts in space, since cosmic rays are harmful to living tissue. By studying how the plasma at the boundary behaves, scientists gain clues to how well the heliosphere protects us. On smaller scales, the physics of the boundary plasma can be broken down into distributions of particle velocities. In plasma, the temperature is not always the same for all particles. Some may move faster along magnetic fields, others across them. These anisotropies can lead to micro-instabilities, which generate waves and heat the plasma. For example, the mirror instability occurs when particles have more energy perpendicular to the magnetic field than parallel. This instability produces fluctuations that scatter particles, redistributing energy and heating the plasma. At the heliosheath, such instabilities could be active, raising the temperature beyond simple fluid predictions. Voyager's data, though limited, hint at such fine-scale physics. The spacecraft was never designed to explore the edge of the heliosphere, yet it has revealed details that touch on deep questions of plasma behavior. By combining these data with theory and simulations, scientists can build a picture of how the solar wind and interstellar medium meet. Simulations of plasma often rely on magnetohydrodynamics, which treats plasma like a conducting fluid influenced by magnetic fields. But in regions like the heliosheath, where kinetic effects, turbulence, and wave-particle interactions dominate, magnetohydrodynamics alone is not enough. More advanced models, including particle-in-cell simulations, are used to capture the complex processes that can explain the extra heat and density. Even within the Sun itself, parallels exist. The solar corona, the outer atmosphere of the Sun, is much hotter than the surface below, a puzzle long known as the coronal heating problem. There, too, processes like magnetic reconnection and wave-particle interactions are thought to be responsible. The similarity to the heliospheric boundary suggests a repeating theme in astrophysics. Whenever plasma interacts with magnetic fields on large scales, heating occurs beyond what simple models predict. This hints at a universal property of plasma, linking the small scales of solar flares with the grand scales of the heliosphere's edge. As Voyager travels deeper, the contrast between the solar plasma and the interstellar medium becomes clearer. The boundary is not a sharp line, but a broad transition filled with waves, shocks, and turbulence. The hotter and denser plasma is a signature of this transition zone, where the laws of plasma physics shape the fate of particles and fields. It is in this zone that the solar system hands over its influence to the galaxy, and it is here that the mysteries of heat and density reveal themselves most strongly. In the heart of plasma microphysics, what matters most is not only how particles move, but also how they interact with collective oscillations of the medium, which are known as plasma waves. Plasma is a medium that supports a wide range of waves because its charged particles and magnetic fields couple together in complex ways. At the edge of the solar system, in the heliosheath and just beyond the heliopause, Voyager measurements showed that plasma oscillations could be triggered by disturbances from the Sun, and these oscillations were used to measure density. But plasma oscillations are not just diagnostic tools. They are also central to how energy is transferred, dissipated, and converted into heat. Different wave modes, such as Langmuir waves, ionoacoustic waves, Alfvén waves, and magnetosonic waves, can resonate with particles and change the distribution of their velocities. These interactions redistribute energy from bulk motion into random thermal motion, raising the effective temperature of the plasma. Langmuir waves, which are oscillations of electrons against a background of positive ions, occur at the plasma frequency, a characteristic frequency that depends directly on electron density. Voyager detected these waves in the boundary region, which not only gave density values but also hinted that strong electron dynamics were present. In plasma, Langmuir waves can be damped by a process known as Landau damping, where electrons moving at nearly the same speed as the wave interact with it, transferring energy from the wave to the particles. This is a form of energy dissipation that requires no collisions, relying instead on resonance. At the heliospheric boundary, Landau damping may act continuously, converting wave energy into heat and explaining why the plasma remains hotter than predicted. Ion acoustic waves are another mode, involving compressions and rarefactions of ions with the electrons providing the restoring force. These waves can also be damped and can exchange energy with ions. Because ions are much heavier than electrons, the heating associated with ion acoustic waves tends to raise ion temperatures. If such waves are abundant in the heliosheath, they could explain part of the unexpected heating of protons and heavier ions carried by the solar wind. The balance of energy between electrons and ions becomes critical, because Voyager's instruments mostly measured electrons, while the state of the ions had to be inferred. In many astrophysical plasmas, ions and electrons are not in thermal equilibrium, with ions being hotter. This disequilibrium may also exist at the boundary, with even more hidden heating in the ions than what the electron data alone show. Alphen waves are of special importance. They are transverse waves that travel along magnetic field lines, caused by the tension in those lines. Alphen waves can carry energy across large distances without much damping, but under the right conditions they can transfer energy to particles. This happens through cyclotron resonance, where particles gyrating around magnetic field lines at their natural cyclotron frequency interact with waves of the same frequency. Such resonances can accelerate particles, scatter them, and heat them. The heliosheath, with its compressed and twisted magnetic fields, may be a site where alphenic turbulence cascades down to smaller scales, feeding cyclotron resonance and heating the plasma. In laboratory plasmas, cyclotron heating is used deliberately to raise temperatures in fusion experiments, where microwaves at the cyclotron frequency of ions or electrons are injected to transfer energy efficiently. The fact that the same principle operates at the edge of the solar system shows the unity of plasma physics across settings as different as magnetic confinement devices on Earth and the vast heliosphere. Magnetosonic waves combine both magnetic and pressure forces, allowing compressive disturbances to propagate in plasma. These waves, like sound waves, but influenced by magnetic fields, can also participate in energy transfer. When shock waves from the solar wind steepen and interact with the heliosheath, they likely generate a spectrum of magnetosonic waves. These waves can break down into smaller-scale turbulence, which then dissipates and heats the plasma. In laboratory conditions, magnetosonic-like modes are observed in plasma devices where density and magnetic fields vary, and they play a role in stability and confinement. By comparing laboratory results to Voyager's data, researchers can test whether the same mechanisms scale up to astrophysical sizes. Energy dissipation in a collisionless plasma is a subtle matter, because unlike in air or water, particles do not collide frequently to exchange energy. Instead, processes like Landau damping, cyclotron resonance, and stochastic interactions with turbulence act as substitutes for collisions. These processes allow ordered wave energy to be transformed into random particle energy, raising temperature. This is why the plasma at the heliospheric boundary can be hotter than models based on collisional fluids would ever predict. In fusion reactors such as Tokamaks and stellarators, similar collisionless dissipation mechanisms are exploited or must be controlled. For example, turbulence in Tokamaks can degrade confinement by transporting energy outwards, while carefully designed resonant heating methods are used to inject energy into the plasma. The heliosheath resembles an uncontrolled version of such an experiment, where turbulence and waves interact naturally without design. Another important microphysical effect is the generation of micro-instabilities. When the velocity distribution of particles is not Maxwellian, meaning it is not the smooth bell curve expected in equilibrium, instabilities arise that can generate waves and heat the plasma. For example, the ion cyclotron instability occurs when there is an excess of perpendicular energy compared to parallel energy relative to the magnetic field. The mirror instability arises under similar anisotropic conditions, producing spatial structures in the magnetic field that trap particles and scatter them. These instabilities are well studied in laboratory plasmas, where diagnostics can track wave growth and particle heating. At the edge of the heliosphere, they likely operate invisibly but effectively, maintaining the hotter and denser plasma detected by Voyager. Comparisons with laboratory plasmas also highlight scale differences. In devices on Earth, plasmas are confined within meters, with particle densities far higher than in space but with lower overall energies. At the heliospheric boundary, plasmas extend across billions of kilometers, with densities of less than a particle per cubic centimeter, but with particles carrying energies far higher than in most laboratory experiments. Despite these differences, the same mathematical descriptions apply based on Maxwell's equations, the Vlasov equation, and magnetohydrodynamics. This shared physics makes laboratory experiments valuable analogues. For instance, magnetic reconnection has been reproduced in laboratory plasma experiments using devices like the magnetic reconnection experiment at Princeton, where scientists study how field lines break and reconnect, releasing energy and heating plasma. The results match processes inferred at the solar boundary, supporting the idea that reconnection helps explain the hotter plasma. In addition to reconnection, turbulence has been recreated in laboratory plasmas. In large tokamaks, turbulence naturally arises as a challenge to confinement, and measurements show cascades of energy from large to small scales, just as in astrophysical plasmas. The same cascades likely occur in the heliosheath, where energy from large-scale solar-wind interactions is broken down into smaller fluctuations that heat particles. Laboratory results demonstrate that turbulence can account for significant heating, and applying this understanding to the heliosphere helps explain why Voyager measured unexpectedly high temperatures. Wave-particle interactions have also been studied in detail in laboratories, particularly in linear plasma devices where controlled waves are launched, and their effects on particle distributions measured. These experiments confirm that Landau damping and cyclotron resonance transfer wave energy into heat efficiently. At the heliospheric boundary, where many wave modes are present at once, such interactions likely dominate the energy budget, leading to the dense, hot plasma observed. Another microphysical process relevant here is stochastic heating, where particles gain energy not through resonance with a single wave but through random interactions with a turbulent field. In this mechanism, particles experience a sequence of small kicks from fluctuating fields, and over time these kicks add up to significant heating. Stochastic heating has been proposed to explain the high temperatures of the solar corona, and it could similarly explain the excess heat in the heliosheath. Voyager's detection of turbulent fluctuations supports this possibility. The role of pickup ions must also be considered at the microphysical level. When neutral atoms from interstellar space are ionized, they suddenly find themselves in the reference frame of the solar wind moving at hundreds of kilometers per second. Their initial motion relative to the magnetic field makes them form ring distributions, which are highly unstable. These ring distributions generate waves, particularly alpha and ion cyclotron waves, which then scatter particles and contribute to heating. This self-generated turbulence by pickup ions is a major source of wave energy at the boundary, and it feeds into the heating of the plasma. In laboratory plasma physics, similar ring beam instabilities are studied when fast ion beams are injected into plasmas, showing how free energy in the distribution drives waves and turbulence. The heliosheath is a cosmic scale example of this same principle. Dissipation of energy in a collisionless plasma can also occur through phase mixing, where particles moving at different velocities gradually spread out in phase space, smoothing structures and effectively converting ordered motion into disorder. This mechanism is subtle but important, and in the heliosheath it could account for part of the temperature increase. Phase mixing is often studied in controlled plasma experiments, where it can limit the efficiency of wave heating. At cosmic scales, it may act continuously to maintain higher plasma temperatures. Plasma physics also emphasizes the importance of distribution functions rather than single temperatures. A plasma may not have one uniform temperature but a range of energies among its particles. Suprathermal tails, where more high-energy particles exist than expected in a Maxwellian distribution, are common in space plasmas. These suprathermal populations can dominate heating and wave generation. At the heliospheric boundary, suprathermal ions from shocks, turbulence, and pickup processes may drive much of the unexpected heating, keeping the plasma hotter than models based on simple thermal distributions would predict. Laboratory experiments with injected beams and fast particles replicate these effects on smaller scales, providing evidence that suprathermal populations are potent drivers of plasma dynamics. The complex interplay of these microphysical processes, waves, resonances, turbulence, reconnection, instabilities, pickup ions, stochastic heating and phase mixing, makes the heliosheath a natural laboratory of plasma physics. The hotter and denser plasma discovered there by Voyager is not an anomaly, but a natural outcome of these processes working together over vast distances and timescales. In essence, what Voyager measured was the fingerprint of plasma microphysics imprinted on the grand structure of the solar system's boundary. The spacecraft carried a magnetometer that could measure the direction and strength of the magnetic field lines, a cosmic ray instrument to detect high-energy particles arriving from distant parts of the galaxy, and plasma detectors that could sense the density, speed, and temperature of charged particles flowing past the spacecraft. By continuously recording and sending these measurements back to Earth, the Voyagers acted like robotic scouts moving into unknown territory. The scientists back on Earth could not see this barrier directly with their eyes, or with telescopes, but they could infer its existence from the way these invisible forces changed as the spacecraft moved along their paths. When Voyager 1 approached the edge of the heliosphere, the region dominated by the Sun's influence, the magnetic field readings started to behave differently. Normally, inside the heliosphere, the magnetic field lines are carried outward by the solar wind, spiraling around the Sun in what is called the Parker spiral. The magnetometer on Voyager 1 had been recording this spiral pattern for decades, with fluctuations caused by solar storms and by the 11-year cycle of solar activity. But as the spacecraft neared the boundary, the field readings showed that the magnetic pressure increased, the field became more compressed, and its direction began to change. It was as if the spacecraft was pressing against a wall made of magnetic tension, a place where the outward push of the Sun's wind was meeting resistance from the interstellar medium outside. At the same time, the cosmic ray detector recorded a dramatic change. For most of its journey inside the heliosphere, galactic cosmic rays were largely kept out by the Sun's magnetic bubble. The density of these high-energy particles inside the bubble is much lower than in interstellar space because the solar wind and its magnetic fields act as a shield, scattering and deflecting them. But once Voyager approached the barrier, the count of cosmic rays suddenly began to climb. The detector picked up more and more of these fast-moving atomic nuclei, some of them travelling close to the speed of light, arriving from deep space beyond the solar system. The rise was not gradual, it was sharp and sudden, suggesting that the spacecraft had crossed a region where the shielding effect dropped away and the cosmic rays could rush in almost unhindered. The plasma detectors added yet another piece to the picture. Deep inside the heliosphere, the solar wind flows outward at supersonic speeds, hundreds of kilometers per second, carrying charged particles from the Sun. But at a certain distance, the wind begins to slow down as it pushes against the thin but resisting material between the stars. The plasma instrument could sense when the density increased, when the speed slowed, and when the temperature of the particles changed. These measurements confirmed that Voyager was no longer in a simple free-flowing wind, but in a place where the charged particles were piling up, colliding, and heating as they struggled against the outer boundary. Each instrument alone gave hints, but together they formed a coherent picture. The magnetometer showed stronger and differently oriented magnetic fields. The cosmic ray detector showed an inflow of galactic particles, and the plasma sensors showed slowed and heated solar wind. The combination of all three told the scientists that the spacecraft was in a transition zone, a barrier that separated the familiar space of the Sun from the unknown reaches of the galaxy. The sudden changes recorded by the instruments were not smooth or steady. Instead, they often came in bursts, jumps, and irregular steps. This suggested that the barrier is not a simple surface like a glass wall, but rather a turbulent, layered region full of small-scale structures. Magnetic reconnection events could tear and reform field lines, creating temporary holes through which cosmic rays could surge. Shock waves from solar eruptions could travel outward and momentarily push or distort the barrier. The instruments detected these time-varying features, showing that the boundary is alive, dynamic, and constantly shifting. One of the most striking observations came in the year 2012, when Voyager 1 crossed into interstellar space. The magnetometer readings at first seemed confusing, because although the intensity of cosmic rays had jumped and the solar wind particles had dropped, the direction of the magnetic field had not rotated as much as expected. This puzzled scientists for years. They thought that once outside, the interstellar magnetic field should have a very different orientation compared to the Parker spiral inside. but the instruments showed that the field direction was nearly the same on both sides of the boundary, although its strength was different. This suggested that the solar magnetic field drapes over the interstellar field, creating a smooth but compressed transition rather than a sharp change. The Voyager data forced researchers to rethink models of how magnetic fields from the Sun and the galaxy interact. The cosmic ray measurements also revealed fascinating details. The energy spectrum of the particles changed as Voyager moved through the barrier. Lower energy cosmic rays, which are more easily scattered, still showed some variation depending on solar activity, even at those great distances. Higher energy cosmic rays, however, flowed in more steadily, unaffected by solar storms. This distinction helped scientists separate the contributions of solar energetic particles from those of true galactic cosmic rays, providing a clearer view of the radiation environment that exists in deep space. The plasma instruments, especially the plasma wave detector, recorded vibrations in the surrounding medium that provided direct estimates of particle density. When solar eruptions sent shockwaves outward, they could be detected years later as they passed by Voyager, compressing the plasma and causing it to ring like a bell. These plasma oscillations gave some of the first unambiguous proofs that the spacecraft had left the heliosphere and entered a denser interstellar environment. The density jumped by nearly 100 times compared to the near vacuum inside the bubble, and the instruments captured these changes in exquisite detail. It is remarkable that instruments built more than 3 decades earlier could still deliver such sensitive measurements. The magnetometers were mounted on long booms to keep them away from the spacecraft's own magnetic fields, and their delicate sensors continued to register tiny changes in field strength measured in nanoteslas. The cosmic ray detectors, using solid-state detectors and proportional counters, could distinguish between protons, helium nuclei and heavier elements, and could measure energies from millions to billions of electron volts. The plasma wave instrument could detect minute fluctuations in electric fields, translating them into sound-like signals that revealed the density of charged particles in the surrounding space. The data returned to Earth had to travel across billions of kilometers, taking more than 16 hours to cross the void at the speed of light. The signals were faint, requiring large radio antennas of the Deep Space Network to pick them up. Yet despite the weakness of the transmissions, the information carried the fingerprints of the barrier in every measurement. Scientists carefully plotted the graphs, looking at the spikes in cosmic ray counts, the kinks in magnetic field lines, and the oscillations in plasma waves, building a layered image of the distant frontier. What became clear through these measurements is that the barrier is not a fixed surface but a region of gradients. The density of cosmic rays, the orientation of magnetic fields, and the flow of charged particles all change over distances of millions of kilometers. Instead of a sharp wall, there are zones where one influence fades while another grows, overlapping and interacting in complex ways. Voyager's instruments were sensitive enough to capture these gradual changes, as well as the sudden jumps, giving scientists a way to map the boundary in both space and time. The scientific interest in measuring the barrier goes beyond curiosity about the solar system's edge. The data help us understand basic plasma physics, the interaction of stellar winds with interstellar gas, and the shielding of cosmic rays that affects both planetary atmospheres and future space travelers. The interplay of magnetic fields, particles, and radiation is a fundamental process that occurs not only here, but around other stars as well. By studying how Voyager's instruments recorded the changes, researchers can test their theories of astrophysical shocks, turbulence, and cosmic ray transport. When examining the magnetic field data, scientists noticed that the field strength outside the heliosphere was about twice as strong as expected. This raised questions about whether the local interstellar medium is compressed by other factors, such as nearby supernova remnants or interstellar clouds. The precise alignment of the fields also suggested that the solar system is embedded in a larger-scale magnetic structure that guides the flow of cosmic rays. Voyager's direct measurements thus connected the microphysics of particle motion with the macrophysics of galactic structures. The cosmic ray data were equally revealing. The isotropy, or uniformity in arrival direction, of the particles outside the heliosphere was different from that inside. This indicated that the heliosphere itself casts a kind of shadow on the incoming cosmic rays, shaping their distribution. By modelling the counts and energy spectra measured by Voyager, researchers could infer how the heliosphere modulates the galactic radiation and how effective it is as a shield. This has direct implications for the radiation environment in the solar system, which affects climate, atmospheric chemistry, and biological evolution over geological timescales. The plasma wave measurements gave insights into the density and pressure of the interstellar medium. By listening to the high-pitched whistles and lower hums in the data, scientists could deduce how tightly packed the electrons were, how they responded to passing shock waves, and how they interacted with the magnetic fields. These plasma oscillations were like seismographs of space, recording tremors in the invisible medium that lies between the stars. Over time, as Voyager continued to move outward, its instruments provided a continuous record of how the barrier behaves. Changes in solar activity launched pressure waves that travelled outward, reaching the spacecraft years later and causing measurable effects. This time delay allowed scientists to connect events on the Sun with responses at the boundary, creating a long baseline experiment in heliophysics. The data revealed how far the Sun's influence can reach and how it fades into the background of interstellar space. The measurement of the barrier by Voyager's instruments can also be seen as a triumph of experimental physics. Building detectors that could survive decades of cold, radiation, and power limitations and still record subtle signals required great ingenuity. Each reading of magnetic fields, each cosmic ray count, and each plasma oscillation was a scientific treasure, collected patiently across distances no human spacecraft had ever travelled before. The fact that these instruments were not originally designed to study the interstellar medium, but rather the outer planets, makes their achievements even more remarkable. The barrier turned out to be more complex and multi-layered than early models had suggested. The instruments showed that instead of a single clean line between solar and interstellar space, there are zones of mixed influence, turbulent structures, and fluctuating boundaries. For decades, astronomers, astrophysicists, and space scientists had tried to predict where this boundary would be located, and what sort of measurements might show that a spacecraft had crossed into the realm of interstellar space. Voyager 1, launched in the year 1977, carried with it sensitive instruments that were never originally designed to survive this far, but which continued to function long after the primary planetary missions were completed. When the spacecraft eventually reached the outermost regions, it began to detect patterns in the magnetic field, the density of charged particles, and the behaviour of cosmic rays that indicated that it had arrived at the long-awaited threshold. The heliosphere is not a simple, smooth bubble, but a dynamic and turbulent environment. It is formed by the solar wind, which is a constant flow of plasma streaming outward from the Sun. This plasma consists mainly of electrons and protons that travel at speeds of hundreds of kilometers per second. The outward-moving solar wind eventually meets the incoming flow of charged particles and interstellar gases from the galaxy, and where they collide, they create a complex set of boundaries. Scientists theorize that there should be a termination shock where the solar wind slows down dramatically, a heliosheath where the slowed plasma becomes heated and turbulent, and then finally a heliopause, the ultimate edge where the solar wind is no longer strong enough to hold back the interstellar medium. Beyond this lies interstellar space, filled with plasma and magnetic fields not shaped by our Sun but by the galaxy as a whole. Voyager 1's crossing of this heliopause boundary was the moment when human-made technology first entered this domain. Voyager 1's instruments were key to identifying the crossing. The spacecraft carried detectors for measuring plasma, although by this stage the original plasma instrument was no longer functioning. Instead, scientists relied on other tools. The plasma wave instrument, for instance, could detect oscillations in charged particles that revealed the density of the surrounding medium. The cosmic ray detectors measured the flux of high-energy particles, both those coming from the Sun and those coming from deep space. The magnetometer could track changes in the orientation and strength of magnetic fields. By combining data from all these instruments, researchers pieced together the signature of crossing the boundary. In particular, they noticed that the number of solar origin particles decreased dramatically, while at the same time the number of galactic cosmic rays increased. This sharp change suggested that the spacecraft had moved into a region no longer dominated by the solar wind. The plasma wave instrument provided one of the clearest confirmations. As Voyager 1 travelled farther from the Sun, the instrument recorded vibrations caused by plasma oscillations. These oscillations have frequencies directly related to the density of electrons in the medium. In the heliosphere, electron densities are relatively low, but in the interstellar medium the density is higher. When Voyager 1 recorded oscillations corresponding to a density several times greater than what would be expected within the heliosphere, scientists realized that the spacecraft had crossed into interstellar space. This evidence became definitive when, in the year 2012, the data showed consistent values matching interstellar conditions. Though the actual crossing may have taken place earlier, the analysis of the measurements allowed researchers to confidently state that Voyager 1 had indeed left the heliosphere. The cosmic ray measurements were equally striking. Inside the heliosphere, cosmic rays from the galaxy are partly deflected and weakened by the protective bubble created by the solar wind. Solar energetic particles, in contrast, dominate the inner regions. When Voyager 1 crossed the heliopause, the detectors showed a dramatic drop in solar particles and a simultaneous increase in galactic cosmic rays. The transition was not gradual but sharp, indicating a well-defined boundary. Galactic cosmic rays are extremely energetic particles, often moving close to the speed of light, and they originate from distant supernova explosions and other violent astrophysical events. The fact that their intensity suddenly rose around Voyager 1 was a sign that the shielding effect of the heliosphere had ended. The magnetic field data presented a more puzzling picture. Scientists expected that the orientation of the magnetic field would change abruptly when moving from the heliosphere into the interstellar medium, since the solar magnetic field has one direction and the galactic field should have another. However, when Voyager 1 crossed the boundary, the magnetic field strength increased, but the direction remained largely the same as before. This caused a debate in the scientific community about whether the spacecraft had truly left the heliosphere. Some argued that it had entered a transitional region rather than full interstellar space. Over time, additional plasma wave measurements and detailed analysis convinced most researchers that the spacecraft had indeed crossed the heliopause, but that the boundary was not as sharp or simple as models had predicted. The magnetic fields at the boundary may be draped and compressed in ways that align them temporarily with the solar field, creating the unexpected measurements observed. The journey of Voyager 1 to this boundary took more than 35 years. Launched in September of 1977, the spacecraft had first explored Jupiter and Saturn, providing close-up images and data that transformed our understanding of the gas giants and their moons. After completing its planetary mission, Voyager 1 continued on a trajectory that would take it out of the solar system in the direction of the constellation Ophiuchus. Its twin, Voyager 2, followed a different path, visiting Uranus and Neptune before also heading outward. Both spacecraft carried the famous golden records, phonograph discs with sounds and images representing Earth, meant as a message to any potential extraterrestrial civilizations. But scientifically, their greatest contribution has been their exploration of the outermost boundaries of the heliosphere. The heliosphere itself is shaped by the activity of the Sun, which changes over the course of the 11-year solar cycle. During periods of solar maximum, when the Sun is more active, the solar wind is stronger and can push the boundary farther outward. During solar minimum, the solar wind is weaker and the heliopause may contract slightly. Voyager 1's crossing therefore depended not only on its distance but also on the timing within the solar cycle. This made predictions difficult since the boundary is not fixed but moves depending on solar activity and on the conditions in the surrounding interstellar medium. The spacecraft's measurements gave scientists the first direct evidence of these variations, allowing models of the heliosphere to be refined. The density of interstellar plasma detected by Voyager 1 revealed much about the environment outside the heliosphere. It confirmed that the local interstellar medium has an electron density of roughly 0.08 electrons per cubic centimetre, which is several times greater than the density inside the heliosphere. This finding was important for understanding the interaction between the solar wind and the galaxy. The data also helped in studying the processes by which cosmic rays are modulated by the heliosphere. By knowing how the flux of cosmic rays changes across the boundary, researchers could better understand the shielding effect of the Sun on Earth and other planets. Galactic cosmic rays are dangerous to both astronauts and spacecraft electronics, so studying their behaviour at the heliopause has practical implications for future interstellar travel. Voyager 1's crossing also raised new questions. For example, why did the magnetic field direction not change as expected? Why was the transition so sharp in terms of particles, but more ambiguous in terms of fields? Were there smaller scale structures and layers at the boundary that models had not accounted for? These puzzles spurred new theoretical work and comparisons with observations from other spacecraft such as IBEX, the Interstellar Boundary Explorer, which maps energetic neutral atoms created at the heliopause. Together, these data sets began to build a more complex picture of the heliosphere as a dynamic, wrinkled bubble, with multiple folds and layers rather than a smooth sphere. The human story behind Voyager 1's crossing is equally powerful. When the spacecraft was launched, few could have imagined that it would still be sending data back to Earth more than 3 decades later. The engineers who built it had to design instruments that could withstand the harsh conditions of deep space, operate with extremely low power, and transmit weak signals across billions of kilometers. By the time it reached the boundary of the heliosphere, Voyager 1 was over 120 astronomical units from the Sun, where 1 astronomical unit is the distance between Earth and the Sun, about 150 million kilometers. The radio signal from Voyager 1 took over 17 hours to reach Earth, traveling at the speed of light. Receiving and decoding such faint signals required enormous radio telescopes of the Deep Space Network, spread across California, Spain, and Australia. The success of maintaining communication with the spacecraft at such distances was itself a triumph of engineering. The moment when Voyager 1 detected evidence of leaving the heliosphere can be thought of as a turning point. It demonstrated that human technology could reach and survive in interstellar space. It provided direct confirmation of theories that had been debated for decades. It revealed surprises that challenged existing models, and it set the stage for future missions that might one day follow Voyager 1 into the galaxy. The spacecraft itself will continue to drift silently outward, its instruments gradually shutting down as its power source weakens. But the data it already sent have given us the first detailed look at the boundary between the Sun's domain and the vastness beyond. Voyager 1's detection of the crossing did not rely on a single measurement, but on a combination of observations that together painted a coherent picture. The decrease in solar particles, the increase in galactic cosmic rays, the rise in plasma density, and the strengthening of the magnetic field all pointed to the same conclusion. Each instrument provided a piece of the puzzle, and together they revealed the signature of the heliopause. The process of interpreting these signals was itself an act of scientific exploration, as researchers had to weigh conflicting evidence, refine their models, and eventually accept that the spacecraft had entered a new realm. The concept of a boundary in space may sound simple, but in reality it is a region of transition. The heliopause is not a sharp wall, but a zone where the influence of the Sun fades and the influence of the galaxy grows. Plasma flows, magnetic fields, and cosmic rays all behave in complex ways at this boundary, creating structures that may vary over time and space. Voyager 1 provided the first in situ measurements of this region, and these data will continue to be analysed for decades. Already, they have shown that the heliosphere is more than just a bubble. It is a dynamic, evolving structure shaped by both solar activity and the galactic environment. The spacecraft's crossing of the boundary was the first step in unravelling these complexities. Voyager 2 confirms the findings, and the way this second spacecraft added its voice to what was first seen by its twin is one of the most fascinating parts of the great human story of exploring the very edges of the solar system. When Voyager 1 crossed into the outer regions and recorded strange shifts in the environment, many scientists believed that a new kind of barrier had been reached. This barrier was not a solid surface like the crust of a planet, but rather a vast and invisible frontier where the winds from the Sun, made up of streams of charged particles, slowed down, thickened, and pressed against the forces of interstellar space. Voyager 1 had given the first hints that such a frontier, sometimes described as a wall, was real. But as with any scientific discovery, a single observation always raises questions about whether it can be trusted fully. That was why the journey of Voyager 2 was so important, for it would arrive at the same boundary by a different path years later, carrying its own set of instruments, and provide either support or contradiction to what had already been suspected. The way Voyager 2 approached the outer edges of the Sun's domain was slightly different from Voyager 1. Whereas the first craft took a more northern path out of the plane of the planets, Voyager 2 followed a more southerly route. This gave scientists the rare opportunity to compare two different slices of the heliosphere, which is the bubble carved out in space by the solar wind. If both spacecraft observed similar changes at roughly similar distances from the Sun, then the case for a consistent, structured boundary would be much stronger. Voyager 2 moved steadily outward, year after year, its instruments still working despite the decades that had passed since its launch in the year 1977. By the time it reached distances of more than 100 astronomical units from the Sun, with each astronomical unit equal to the distance between Earth and the Sun, it began to record changes that mirrored those seen earlier by its twin. The data from Voyager 2 showed that as it neared the edge of the heliosphere, the density of plasma increased sharply. The solar wind, which had been moving supersonically away from the Sun for billions of kilometers, slowed down and became hotter and more turbulent. At the same time, the number of galactic cosmic rays entering the spacecraft's detectors began to rise. These cosmic rays are high-energy particles, often protons or heavier nuclei, that originate from violent events in distant galaxies, such as supernova explosions. Inside the heliosphere, the pressure from the Sun's outflow partially shields against these rays, but as Voyager 2 moved past the outer edge, the shielding weakened, and the true flux of galactic cosmic rays could be measured more clearly. This was one of the main signals that a boundary had been crossed, for it showed that the spacecraft was leaving the relative safety of the Sun's bubble and entering interstellar space itself. The rise in cosmic rays measured by Voyager 2 was strikingly similar to what Voyager 1 had recorded, though the exact timing and details showed some differences. These differences themselves were valuable, for they indicated that the boundary was not perfectly uniform. Rather, it might be shaped by the local magnetic fields of the galaxy, by the changing rhythm of the solar cycle, and by the constantly shifting streams of charged particles flowing outward from the Sun. Still, the core pattern was unmistakable. Both spacecraft had seen the sudden increase in cosmic ray counts, and both had registered a drop in the number of solar particles, confirming that a major transition had occurred. This was the scientific equivalent of finding the same geological layer in two different excavation sites, showing that there was indeed a real and repeatable structure at the edge of the heliosphere. The magnetic field data from Voyager 2 also supported the findings. When Voyager 1 crossed the boundary, there had been much debate about the direction and strength of the magnetic field. The instruments on Voyager 1 were still working but had limitations, and some scientists argued that the crossing might have been more complex than it first appeared. When Voyager 2 later crossed, its magnetometer readings also showed a sudden change, not only in the intensity of the field, but also in its stability. The region beyond the heliosphere had a stronger and more consistent interstellar magnetic field, which guided the flow of cosmic rays and shaped the outer skin of the Sun's bubble. With both spacecraft providing measurements from different regions of space, the evidence became stronger that the wall-like boundary was not just a random fluctuation, but part of the natural architecture of the solar system's frontier. Voyager 2 also carried a working plasma instrument, which Voyager 1 had lost decades earlier. This turned out to be a crucial difference, for it allowed Voyager 2 to measure directly the density, temperature, and speed of the plasma it encountered. As it crossed into interstellar space, the plasma instrument detected a sudden increase in density, exactly as would be expected if the spacecraft were entering a region where the interstellar medium pressed back against the weakened solar wind. The density values recorded by Voyager 2 were consistent with what had been inferred indirectly from Voyager 1's measurements of plasma oscillations. Having this direct confirmation gave scientists far greater confidence in their models. It was like finally hearing the sound of water rushing into a cave after years of only seeing faint dampness on the walls. The concept of the wall was further strengthened by the timing of the transitions. Voyager 2 crossed the heliopause, which is the technical term for the boundary, in the year 2018. Roughly 6 years after Voyager 1's crossing in the year 2012. The fact that both spacecraft encountered the transition at comparable distances from the Sun, even though they were separated by more than 100 astronomical units along different paths, argued strongly that the boundary was a real and global feature of the heliosphere. At the same time, the slight differences in crossing distance, with Voyager 1 leaving at about 121 astronomical units, and Voyager 2 at about 119 astronomical units, revealed that the heliosphere is not a perfect sphere, but may be squashed or elongated depending on the pressures of the interstellar medium and the Sun's activity. In scientific research, replication is everything. A single experiment or a single probe can provide amazing insights, but it always carries the risk of being an exception, an anomaly, or the result of instrument error. When Voyager 2 confirmed the main findings of Voyager 1, it transformed the discovery from a tantalizing possibility into a reliable fact. The two spacecraft together painted a picture of the heliosphere as a great bubble with a defined outer skin, a skin that resists galactic cosmic rays, bends magnetic fields, and marks the true border between the Sun's influence and the larger galaxy. This border may appear invisible to human eyes, but to the sensitive detectors of the Voyagers, it revealed itself through patterns of particles, waves, and fields that could be measured, analysed, and compared. Voyager 2's journey also provided valuable information about the thickness of the boundary region. The crossing was not like passing through a sharp and instant wall, but more like moving through a layered transition zone. Over the course of several days and even weeks, the instruments detected gradual changes, such as the fading of solar particles, the strengthening of interstellar plasma signals, and the alignment of magnetic fields. This gradual but decisive passage gave scientists a chance to study how two vast regions of space interact, and how energy and matter flow across their boundary. It also hinted that the heliopause might ripple or shift with time, pushed inward and outward by changes in solar activity. The plasma oscillations detected by Voyager 2 offered another piece of evidence. These oscillations are like the ringing of a drum when it's struck. In space, they occur when energetic particles excite waves in the plasma, which can then be detected as variations in electrical potential by the spacecraft's instruments. Voyager 1 had recorded such oscillations beyond the heliopause, which had been used to estimate the density of the local interstellar medium. When Voyager 2 recorded similar oscillations, and when the density values matched closely with those earlier estimates, it showed that the spacecraft were indeed sampling the same kind of environment. The interstellar medium was not just a theoretical idea, but a measurable reality, pressing against the Sun's expanding winds and shaping the edges of the solar system's domain. Another striking aspect of Voyager 2's confirmation was the way it illuminated the dynamic balance between the solar wind and the interstellar medium. The heliosphere exists because the solar wind has enough energy to push back against the gas, dust, and magnetic fields that fill the galaxy. But this balance is delicate, and at the outer edge, it tips in favour of the interstellar medium. Voyager 2's plasma data showed precisely how the density increased, how the flow slowed, and how the direction of particle movement shifted. This was like watching the tide turn at the shoreline, with the outward surge of the Sun's plasma finally yielding to the incoming push of galactic matter. The data also raised new puzzles. For example, although the cosmic ray flux increased sharply beyond the boundary, there were still signs of modulation, suggesting that the heliosphere's influence might extend further out than expected, or that the interstellar medium itself has its own variations and turbulence. Voyager 2's instruments were sensitive enough to detect these subtle patterns, providing fresh challenges for theoretical models. The very idea of a wall, then, may be less like a rigid partition and more like a dynamic membrane, stretched and rippled by competing forces, yet still marking a clear separation between inside and outside. The fact that Voyager 2 confirmed the findings also carried implications for other areas of astrophysics. If the heliosphere has such a structured and measurable boundary, then other stars with their own stellar winds must also have similar protective bubbles. The study of how these bubbles interact with their galactic environments can help explain how radiation environments vary from star to star, and how planetary systems may be shielded from or exposed to cosmic rays. Voyager 2, by confirming the wall around our own Sun, effectively opened a new chapter in comparative astrospheres, where scientists can apply what has been learned here to other stars seen through telescopes. The robustness of Voyager 2's confirmation also came from the consistency of its multiple instruments. It was not just one measurement that matched Voyager 1's earlier data, but several: the plasma density, the cosmic ray flux, the magnetic field changes, and the disappearance of solar wind particles. Each of these was like a separate witness in a courtroom, describing the same event from a different angle. Together they built a coherent case that the wall-like boundary existed and that the spacecraft had indeed crossed into interstellar space. The details of the particle measurements from Voyager 2 also added nuance. For instance, as it crossed the boundary, the spacecraft recorded that the population of energetic particles originating from the Sun dropped off rapidly, replaced by a steadier flux of galactic particles. The energy spectra of these particles showed clear differences, with solar particles typically less energetic and more variable, while galactic cosmic rays had higher energies and more consistent distributions. The shift in these spectra was another fingerprint of the transition, further strengthening the evidence. In a way, Voyager 2's confirmation was like the second stroke of a clock. The first strike from Voyager 1 had startled the scientific world, signalling that the hour of interstellar exploration had arrived. But one strike alone could be doubted. The second, from Voyager 2, echoed across the silence of space and made the passage undeniable. The existence of the wall, the heliopause, was no longer a matter of speculation but of measured fact, supported by two independent and complementary journeys. The wall is not uniform. Its shape and position may change with solar cycles, and its interaction with the galaxy's magnetic fields may create complexities that we are only beginning to grasp. The data show hints of layers, ripples, and unexpected fluctuations, suggesting that the boundary is more like a living skin than a static shell. Future missions may one day map it in greater detail, but for now it is the twin Voyagers, with their decades-old instruments still faithfully working, that continue to provide the only direct measurements from this remote frontier. Voyager 2 confirmed the existence of the wall, not by repeating every detail exactly, but by showing the same essential structure from another angle, with complementary instruments that added fresh insights. The spacecraft's plasma data, magnetic field readings, and cosmic ray counts all aligned with the earlier discoveries of its twin, weaving a consistent picture of the solar system's edge. This scientific story, unfolding across decades and billions of kilometers, remains one of the most remarkable achievements in the history of exploration. Beyond the wall of the solar bubble lies a region that is unlike any part of space we can directly sense from Earth. This area is called interstellar space, and it begins just past the invisible border where the solar wind, the endless stream of charged particles blown out from the Sun, finally loses its power against the much older and much more stable gases, dust, and radiation fields that belong not to our solar system, but to the galaxy as a whole. For billions of years, this border has been there, marking where the influence of the Sun ends and where the collective environment of the Milky Way begins. The Voyager spacecraft, launched in the late 1970s, have carried humanity's instruments across this shifting boundary, allowing us for the very first time to gather real data about what lies beyond the solar bubble. Interstellar space is not empty, though from the perspective of human senses it might appear like a complete void. The density of matter is so low that within a cubic centimetre of space there might only be a handful of atoms, and those atoms are not the same as those trapped by the solar wind. Instead, they are part of the interstellar medium, a mixture of hydrogen atoms, helium atoms, traces of heavier elements, cosmic dust grains, magnetic fields stretched across unimaginable distances, and high-energy cosmic rays that were born in violent stellar explosions far away. This medium fills the space between the stars, binding the galaxy together in a sea of plasma and radiation. When the Voyager spacecraft crossed out of the solar bubble, they began to taste directly the difference between the solar wind plasma and the galactic plasma, and in those measurements lies the story of how a star's personal environment blends into the wider cosmos. The first important clue about what lies outside the wall came from changes in particle counts. Inside the solar bubble, charged particles from the Sun dominate. They are relatively low in energy compared to the galactic cosmic rays, and they form a kind of shield, reducing how many external cosmic rays can penetrate deep inside the heliosphere. Once Voyager stepped outside, the situation shifted dramatically. Instruments that count incoming high-energy particles suddenly registered a sharp rise. This rise was evidence that the shielding effect of the Sun's outflow had ended. Beyond the wall, galactic cosmic rays, which are atomic nuclei and electrons accelerated to near the speed of light by ancient supernova shock waves and other energetic events, roam freely. These cosmic rays can be dangerous to both electronics and living tissue because of their immense energies, and one of the reasons scientists are interested in the Voyager's data is that it helps them understand how such radiation might affect future long-distance space travel by humans. But cosmic rays are only part of the picture. Another crucial measurement concerns plasma density. The Voyagers carry instruments capable of detecting oscillations in plasma when it is disturbed by solar activity. Inside the heliosphere, the plasma density is much lower than in the interstellar medium. When Voyager crossed into interstellar space, it found that the plasma density around it was many times greater than what it had measured just inside the wall. This was one of the strongest signs that the spacecraft had truly left the Sun's domain and entered the galactic domain. Yet even with this higher density, the interstellar medium is still almost a perfect vacuum compared to anything we can create on Earth. The magnetic field is another element that gives structure to the region beyond the solar bubble. The Milky Way's magnetic field threads through interstellar space like invisible lines of force, twisting and bending around clouds of gas and interacting with shock fronts from supernovae. Voyager's magnetometers detected subtle changes in the direction and strength of magnetic fields as they crossed the boundary. These changes were not as dramatic as scientists had expected, which has raised questions about how sharp or gradual the true transition is between the heliosphere and interstellar space. The fact that the direction of the magnetic field did not shift as sharply as predicted suggests that the Sun's influence may extend further than once believed, or that interstellar fields themselves are shaped in complex ways by the Sun's motion through the galaxy. Another fascinating aspect of interstellar space is that it carries a record of the history of the galaxy. The atoms and ions drifting there may have been forged in stars that lived and died billions of years ago, their ashes scattered across the spiral arms of the Milky Way. Traces of heavy elements like oxygen, carbon, and iron in the interstellar medium are products of nuclear fusion inside those long-dead stars. Each time Voyager samples the environment, it is in effect touching the ancient remnants of stellar furnaces. That idea adds weight to every bit of data the spacecraft sends back, for it is not only mapping a boundary, but also whispering the story of countless generations of stars. What lies beyond the wall is not static. The Sun itself is moving through the galaxy at roughly 220 kilometers per second, orbiting the galactic center once every 230 million years. As it moves, the shape of the heliosphere changes, compressed in the direction of travel and elongated behind like the wake of a ship. The region of interstellar space into which the Voyagers have entered is just one patch of the wider galactic medium, and it may not represent the whole. Over millions of years, the Sun will pass through clouds of denser gas, regions with stronger magnetic fields, or even bubbles carved out by past supernovae. Each environment would alter the shape of the heliosphere, meaning that the wall the Voyagers crossed is just one version of a border that is always shifting with time and location. Scientists also think about shock waves that travel through interstellar space. When a star explodes in a supernova, it sends out a blast of material moving at thousands of kilometers per second, compressing and heating the surrounding gas. These shock waves can travel for light years, stirring up turbulence in the interstellar medium and accelerating particles to cosmic ray energies. If such a shock wave were ever to pass near our solar system, it would distort the heliosphere drastically and possibly expose the inner planets to higher levels of radiation. By studying what Voyager sees in its current position, scientists can estimate how well the heliosphere can protect us from such galactic events. The Voyager's journey also raises questions about the balance between different forms of energy in interstellar space. There is thermal energy from the random motion of particles, magnetic energy from the galactic field, and kinetic energy from large-scale flows of gas. Understanding how these energies interact is essential for building models of how galaxies evolve. For example, when interstellar gas clouds cool and collapse under gravity, they can form new stars. But magnetic fields and turbulence can slow this collapse. The data from Voyager, though coming from only a single point in space, helps test these models by giving direct values for density, temperature, and field strength. There is also the mystery of interstellar dust. Tiny grains of carbon, silicates, and ice float between the stars. Some of this dust drifts into the heliosphere, where spacecraft like Ulysses and Cassini have detected it. Beyond the wall, dust grains are more common, though still incredibly sparse compared to anything familiar on Earth. These grains are important because they are the seeds around which new planets and stars eventually form. Voyager's instruments are not highly sensitive to dust, but the spacecraft has been struck by occasional tiny particles, and those impacts help confirm the nature of the medium through which it travels. Another factor is the background radiation that permeates interstellar space. This includes not only the galactic cosmic rays, but also faint radio emissions and even traces of the cosmic microwave background left over from the Big Bang. Voyager does not carry instruments tuned to measure all of these directly, but its plasma wave instruments can detect some natural radio signals generated by interactions between plasma and magnetic fields in space. These signals tell scientists about large-scale structures and shock waves propagating through the interstellar medium. Temperature is another subtle but vital aspect. In interstellar space, the gas is not at a single uniform temperature. There are cold, neutral regions with temperatures of only a few tens of degrees above absolute zero, warmer ionized regions with temperatures of thousands of degrees, and hot coronal gas with temperatures of millions of degrees. Voyager is sampling one of the warmer ionized regions, where the plasma temperature is tens of thousands of degrees. Because the density is so low, however, this does not mean the spacecraft is being heated. The few particles it encounters carry high energies, but there are too few of them to transfer noticeable heat to the spacecraft. The role of turbulence also fascinates scientists. In fluids and plasmas, turbulence refers to chaotic, swirling motions that mix energy across scales. The interstellar medium is known to be turbulent on scales from light years down to kilometers. This turbulence can scatter cosmic rays, influence how magnetic fields are arranged, and help determine how stars form from collapsing clouds. Voyager's instruments, by recording fluctuations in magnetic fields and particle densities, are giving the first in situ glimpse of this turbulence. Though the data is limited, it suggests that interstellar space is far from calm, but instead alive with restless shifting patterns. The crossing of Voyager into interstellar space also allows scientists to test long-standing theories about the heliosphere's structure. For decades, models predicted how the Sun's wind should interact with the galactic medium, but until the spacecraft crossed the boundary, those models could not be confirmed. The actual data has already revealed surprises, such as the thickness of the boundary layer and the persistence of solar influence even beyond the supposed edge. Every year, as Voyager continues to send back signals, these models are refined. The spacecraft are also teaching us about how signals travel through interstellar space itself. Radio transmissions from Voyager must cross billions of kilometers to reach Earth, passing through both the heliosphere and the interstellar medium. Along the way, they can be scattered, delayed, or weakened by plasma effects. By carefully studying these signals, scientists learn not only about the spacecraft's condition, but also about the medium itself. The very act of communicating with Voyager doubles as an experiment in galactic plasma physics. Voyager's entry into interstellar space has philosophical weight as well. For the first time, a machine built by human hands has left the direct domain of our Sun and is sailing into the space between the stars. The spacecraft are tiny emissaries, carrying instruments that translate the whispers of atoms, fields, and rays into streams of numbers that scientists can interpret back on Earth. Beyond the wall, one also finds the boundary conditions for how galaxies evolve. The interstellar medium, though faint and diffuse, is the raw material out of which future stars and planetary systems will form. It is constantly enriched by supernovae and stellar winds, stirred by turbulence, and sculpted by gravity. Voyager's data provide a small but direct sample of this ongoing galactic process. By comparing what it finds with observations made by telescopes from afar, astronomers can connect the local with the universal, grounding their models in hard evidence. The two Voyager spacecraft, though launched with different trajectories, are together writing complementary chapters of this exploration. Voyager 1 crossed into interstellar space in the year 2012, while Voyager 2 followed in the year 2018. Their instruments overlap but are not identical, so between them they cover different aspects of the environment. For instance, Voyager 2 still has a working plasma instrument, which Voyager 1 no longer has, so its data on density and temperature are especially valuable. By comparing the two sets of readings, scientists can see how interstellar space looks in slightly different directions, and test whether conditions are uniform or variable. One challenge in studying interstellar space is that the Voyagers are moving slowly relative to galactic scales. They travel at only about 17 kilometers per second, which is fast compared to human standards, but tiny compared to the size of the galaxy. This means that they will take tens of thousands of years just to reach the nearest stars. Yet even within a few decades of travel, they have crossed into regions that had never before been measured directly. Each year adds another slice of data, showing how conditions shift with distance. Another subtlety lies in the role of solar activity cycles. Every 11 years, the sun's magnetic field flips and the solar wind changes in strength. These changes propagate outward and can eventually reach the boundary with interstellar space. Voyager, even beyond the wall, can still detect echoes of these cycles as shock waves and pressure pulses moving outward. These disturbances allow scientists to probe the density and elasticity of interstellar plasma, almost like tapping a wall to hear how solid it is. Some scientists even think about the possibility of Voyager encountering larger interstellar structures in the future. The galaxy is filled with giant molecular clouds, supernova remnants, and other regions where density, magnetic field, and radiation differ sharply. Though the spacecraft are unlikely to reach such regions within human lifetimes, their path may eventually take them into slightly denser or more turbulent areas, providing new kinds of data. For now, they drift through what seems to be a relatively calm but still scientifically rich part of the local interstellar cloud. It is also worth considering the long timeframes involved. The power sources of the Voyagers are radioisotope thermoelectric generators, which slowly lose their output as the plutonium fuel decays. By the late 2020s and early 2030s, most of the instruments will fall silent one by one. Eventually only a carrier signal may remain, and after that the spacecraft will be mute, continuing their journey in silence. Yet even after that, their presence in interstellar space will remain a fact of history, and their data up to that point will continue to shape our understanding. Interstellar space also contains neutral hydrogen atoms that produce a characteristic radio emission at a wavelength of 21 centimeters. Telescopes on Earth and in orbit have long studied this emission to map the structure of the galaxy. Voyager itself does not have a receiver for this wavelength, but its measurements of plasma density and particle counts can be compared to those maps, linking the large-scale view with the local in-situ data. This cross-comparison deepens the scientific value of both types of observation. There is another layer of complexity: interstellar chemistry. Though the medium is thin, it contains molecules such as carbon monoxide, water, ammonia, and even more complex organic compounds. These molecules are often found in denser clouds, but traces are spread widely. They form on the surfaces of dust grains or in gas phases under the influence of radiation. Understanding this chemistry is crucial for piecing together how the ingredients of life are distributed through the galaxy. The interstellar medium also interacts with the sun's motion in a way that generates a bow wave, or perhaps a bow shock depending on the speed and conditions. This is analogous to how a boat moving through water generates a wave at its prow. Voyager's data helps determine whether such a bow shock exists ahead of our solar system. Current evidence suggests that the sun moves more slowly relative to the local medium than once thought, producing only a gentle bow wave rather than a sharp shock. This finding has implications for how cosmic rays and interstellar gas flow around the heliosphere. In studying interstellar space, scientists also confront the issue of scales. Processes happening on the smallest scales, such as interactions between individual charged particles and electromagnetic waves, can influence the larger scales, such as the overall structure of galactic arms. Voyager's plasma wave observations capture some of these microphysical processes, showing how particles resonate with waves and transfer energy. This connects laboratory plasma physics on Earth with galactic astrophysics on scales of light years.